All right, that probably works. The connection is excellent, which is great. Hello everyone. This is a Vulkan stream, or more specifically, this is a Vulkan 1.2 stream, where we'll talk about the new features that were added in Vulkan, what does this mean, why these features are useful, etc. We will not really write any code on stream. There's like code that we could be writing. For example, I don't know, like maybe if this goes really, really fast, which I somehow doubt, we'll write a bit of code, but I don't think so. But there is like a space for writing code with Vulkan 1.2 in the sense that the project that I was streaming before, like last year, or when was this? 2018 actually. Niagara, it actually uses a few features that Vulkan 1.2 makes nicer. So, but anyway, that's not kind of the point of the stream today. The point of the stream today is to talk about Vulkan 1.2. So, if there are any questions on topic, feel free to ask them in chat as we go. Yeah, we'll see. So what are we talking today, right, about? So there is a Vulkan 1.2 release that happened on January 15th, so 3 days ago. And it's an incremental release. So it's not a huge, big thing where here's a completely new graphics API that you have to adapt your code for. It's an incremental release. So this means that Kronos took the existing version of Vulkan, which was 1.1, and then added features to that, and then that became 1.2. There is a list of features that were added to 1.2, and this is kind of what we are going to talk about today. So let me copy this to our working document. And we will kind of talk about all of these things, but not in sequence, because there is actually a few distinct categories of why these features were added in the first place. There's also a few other things that were added. So I'll briefly talk about this PRV stuff. So I'll copy that here as well. I'll talk about this. Wait. Okay. I think the rest is not. Yeah, the rest is honestly not super interesting because it's going to be covered as part of this. So let's first start with a question. What does it mean that Vulkan 1.2 added a lot of these features? Does it mean that there are some devices that used to be able to run Vulkan 1.1 but can't run Vulkan 1.2 anymore? The answer is no. And so the reason why the answer is no is that most of these features are actually optional in 1.2. So what this means is that they are easier to use in 1.2. You don't have to load extensions. You don't have to instantiate like extension structs, and there's like some amount of code that gets a bit simpler. But fundamentally, it doesn't mean that if you have 1.2, you have all of these features. There are a few features that are required. Let me mark them off on that list. So hold on. I'll have to find them in the list. So this one is required, and then subgroup broadcast dynamic ID is required, and Imageless frame buffer, which is nice. Separate depth stencil, host query reset, and timeline semaphores. All right, so that's kind of what this looks like, right? There's like 6 things that are required, and everything else is optional. Oh wait, how come Some other things, I'm assuming key share driver properties is probably also required. It's just not like listed here because it's not a feature, it's an extension. And some other things are as well. So it's not quite a complete list. But like, for example, there are some things here that we will talk about, like descriptor indexing, which is used for bindless rendering. And that's not guaranteed to be supported at 1.2. You still have to check if it's available, which is both good and bad. It's good because it means that you can actually use 1.2 features on a larger set of devices because it's just a driver update, right? The vendors just have to release a new driver. It's bad because it doesn't mean, oh, hey, the device supports 1.2, awesome, I can use feature X or feature Y. So it's a bit of a trade-off. That's kind of what it is, right? So, if yeah, hey, can we like not ask questions about Roblox, please, on the stream? The stream has nothing to do with Roblox. I will take measures if people persist. This is not about Roblox. This is about Vulkan. I'm not answering Roblox questions on the stream. So let's get into this. Let's start talking about some of these features and kind of why they exist and what they can do for people who use Vulkan. And my intention is to go through the entire list, right? So for every single thing, we'll talk about this, even if it's like 1 minute. So where should we start? So let's start with a few extensions, and I will outline them, and then we'll cross over things that we have talked about. So I want to talk about the 8-bit storage. I will save buffer device address for later a bit, but it's kind of related, but I'll talk about this separately. And then this guy, and then this guy, and then this guy. Oh, there's maybe one extension that we will not talk about much at all, which is Vulkan memory model, but whatever. So why do I want to talk about these first? Because to me, they kind of form a theme, and the theme is getting closer to running C code through Vulkan on the GPU. So what do I mean by that? Historically, in the shader code, everybody used the language that is close to C, but there were substantial restrictions in the language as to what types are available, what functionality is available, etc. So one particular problem that has plagued the entire community for years and years and years is that maybe I should. No, you know what, it's fine. I will use this as a scratch space and I'll move things around. So the first problem is that the types that are available in shaders historically are float. This used to be it. Like, there were no other types available for a fair amount of time. And then with DirectX 10, I think, we finally got int, which is nice. And that's still kind of it. And you have float types, and you can compose these types into structures. So you can make a struct that say has, so I will put a struct like light, right? And let's say it has float 3, and I will use HLSL syntax, which is a bit closer. It's all roughly the same, but like I will use HLSL syntax, it doesn't really matter. So we have float 3 position, and we have float 3 color. I'm not sure why I'm using this color for this, but whatever. The problem is if you define the exact same struct on the C side, the layout in memory of the struct is different. So in C, if you were to define the structure using the naive definition of the float 3 type, which is like 3 floats, right? This structure has 6 floats, straightforward. So it should take like 24 bytes. However, on the GPU side, if you were to put this structure into a uniform buffer or into another buffer, it usually pads the data to the 16-byte boundary, because historically GPUs used to use 4 float vectors as the foundation for like everything, for computation, for storage, for everything. So it's kind of a historical limitation that persisted through this day. So what this means is that like here and here, there is extra padding, which is 4 bytes. And so you have a struct definition on the C side, you have a struct definition on the shader side, but it's hard to keep them in sync. And then the other problem is, well, if you wanted to, oh, and there is like egregious examples of this, where if you have float f10, like an array of 10 floats, right? Before one of the extensions in this list, actually the uniform buffer standard layout, if you were to put this in a uniform buffer, it would take 10 float 4 vectors. So it would take 40 floats instead of 10 floats, which is a giant waste of space. And also it's really counterintuitive. It's like you write code like this, code doesn't work, and then you don't know why. But then the other thing is, what if float is too big of a type to use? What if you want a 16-bit floating point number, or 16-bit integer number, or an 8-bit integer number, right? So maybe I want to say, maybe I want to say int 8, like G8, and I kind of want this to take 8 bytes. But up until recently, you couldn't even write this code. And then if you do write this code, can you perform computations on this integer 8 type, right? This is like a fully functional type. So all of these are things that were taken for granted in the C world for decades, right? But in the shader world, mostly this has not been true. So all of these extensions in tandem that I have highlighted, they fix, or they basically fix this problem for good. Oh, there's one other extension that is in a similar theme actually, which is this guy. What all of these extensions mean, once you enable them, if they're available in your device, which is not guaranteed, right, is you can pack the data on the C side using this thing called scalar block layout, which basically says a struct on the shader side that's marked with the appropriate attributes is laid out roughly as it is on the C side, right? The same packing rules. And you can put integer 8 there, and you can put integer 16 there, so like 8-bit, 16-bit integers, and all of this should work. And you can do math with that. So let me briefly... Yeah. So this eventually, right, hopefully will be the standard everywhere. Right now, it's like it requires special driver support, of course, and then maybe in some cases it requires special hardware support. There used to be this problem in DX11, I guess, even, I think, where so yeah, I think NVIDIA recommends padding structured buffers to 16-byte aligned boundary, because otherwise the accesses kind of straddle 16-byte blocks, because my assumption is NVIDIA hardware still cares a bit about the 16-byte alignment. So there is like some growing pains. It'll take us some time to actually get to full support of this. But this is what these extensions do. So with the, let me quickly go through each one of them. So 8-bit storage, and I'll cross them out. 8-bit storage says you can use integer 8 type as a type in the buffer, so in uniform buffers or storage buffers that you read in the shaders. We actually use this in Niagara, so I will not talk much about this, but if you look at the shaders that we were using, I think, yeah, so like we have this meshlet struct, right, and it has vector3, center float radius, and then it has like 4 bytes worth of data that stores the cone, and then some other stuff, right? And this is just 8-bit integer types. This is the same. We are not using the scalar block layout. It was not available at the time, so there's still some kind of alignment concerns here that the code carefully works around. And actually, I think if memory serves, during the development of the streams like 2 years ago, we actually hit a problem, or like 1.5 years ago, I suppose. We actually hit a problem with some of this alignment where I missed something. Something was different between C and GLSL, and I couldn't, like, it took me a while to figure out what was wrong. If we had scalar block layout, we wouldn't have this problem. It would be the same layout rules. So 8-bit storage we actually did use even on stream. So that's cool. Float. So the uniform buffer standard layout is kind of less interesting because it cleans up rules around arrays of floats. It is interesting because the on the DirectX side, scalar block layout isn't really available from what I know yet. But the standard layout is closer to how the X11 layout rules work. So that makes it easier for you to port code between like the DirectX and Vulkan in some cases. But this is by itself like not honestly very interesting. The really interesting one is the scalar block layout, because that is the extension that gives you this property that says if you have a float 3, it's not aligned, it doesn't force like a 16-byte alignment somewhere else, it's just aligned by 4 bytes, just as it would be in C. I should mention that Metal uses C++ for like the shader code, right? So it has C++ rules, but in Metal float 3 type, I forget what they call it, but it's actually aligned to 16 bytes using the C alignment rules, and that's a complete mess. It's like it's so hard to deal with. In the development of our Roblox renderers, we spend so much time kind of fighting the Metal alignment rules versus GLSL alignment rules versus HLSL alignment rules versus C alignment rules. It's insane. Like, I'm really hoping that at some point in the future, just like everybody supports the equivalent of scalar block layout, and we can just forget that this problem ever existed. It'll probably take like 10 years before this happens, but hey. And then, so float 6 int 8 extension, float 16 int 8 extension. In addition to saying, hey, you can store this type somewhere, which is what the storage extensions do. Oh, and by the way, there's no 16-bit storage. This is because it was actually standardized in Vulkan 1.1, so in the prior version. So float 16 and 8 goes one step further. It says, well, not only can you load these types, but you can also work with these types in your shader. We actually also, I think, hit some issues with this when we did Niagara, because once you have these types, right, it's really tempting to write some code that uses these types accidentally, and then that's not permitted by the current set of extensions. I think the problem that we run into is along the lines of, like, you cannot do a direct cast from uint. I'll make the font a bit bigger, by the way, if it's hard for people to read. So I think the problem was along the lines of, like, you cannot cast from uint 8 to float. You can only cast to int and then to float if you don't have this float 16 and 8 extension, because it wasn't even available at the time, so it's like nothing to talk about, right? And so it was really, really easy to accidentally write shader code that is incorrect, but also it's not always the case that the shader code would be correctly validated as being incorrect, so I think we spent some amount of time kind of dealing with that as well. So with that extension, these types, the integer 8, the float 16, the int 16, they work a bit more like just normal types, like you can do whatever you want with them, and less like these magical weird things that you can put in structs in your storage buffers but not do anything else with them. And the final thing is the subgroup extended types. We'll talk a bit about subgroups in the relation to the broadcast dynamic ID. I don't want to talk too much about this right now, but the idea there is the same, where there are some subgroup operations. This is like a magical construct that allows you to pass data between individual threads that run on the GPU. And they were specified in Vulkan 1.1 as working on 32-bit types, and this, I think, allows them for 8 and 16-bit types as well. So this is kind of the same thing in the same vein. Let me briefly look at chat. So I'll cover this create vertex shader stuff maybe a bit later. Definitely Vulkan right now is not heading in this direction. I think that's for a good reason. Is 8-bit integer limited GL cell can find 8-bit HL cell types? That's a good question. I don't know what the HLSL story is for this off the top of my head. On the stream when we worked with all of this, we use GLSL for like various reasons. So I don't know. This may not be supported in the GLSL yet. Oh, but like I think I saw there was definitely some work on the DXC side, at least with float. Let's see. Doesn't talk about 8-bit scalar types yet, but so this is the page that I would refer to with regards to kind of HLSL world. It looks like with shader model 6.2 there's going to be 16-bit scalar types, and this is in Vulkan they kind of appeared between Vulkan 1.1 and 1.2. So is there a shader model 6.3 yet? So this is ray tracing, and then 6.4. Kind of less up to date on the DirectX now because a lot of my newer work is with Vulkan. It doesn't look like this. So it looks like HLSL has some support for 16-bit types, and I'm assuming this will work when targeting Vulkan as well, but doesn't look like it has 8-bit types yet. So I guess maybe we'll have to wait till like shader model 6.5 or something. I think the world is moving in this direction. It's just a question of like when do individual APIs get there. How is the scalar block layout working? Does the driver do alignment, or is the memory really the same as in the C struct? The memory is the same as in the C struct, because see, the problem is, or not the problem, like the thing is, many GPUs don't actually truly care how kind of what the alignment of your vectors is, etc., because it's not really the case that the only thing that a modern GPU can do is read a 16-byte aligned memory block from your uniform buffer or something, right? And it's not even the case that, so it used to be that you had this float relight, right? And then somewhere in your shader you said L light point like position, right? And it used to be the case that in the shader, all the way throughout the GPU stack, like in the target ISA, there was a 4 float, so 16-byte register with 4 floats that would be loaded from this, right? And then you could do math on this register. But these days, GPUs are scalar. All modern GPUs are scalar, which means that on the GPU, the values that the individual thread on the GPU works with are scalars. They're not like vectors of 3 floats or 4 floats. And this terminology gets really confusing when we talk about how GPUs actually work, which we'll actually talk a bit later in the stream. But that's not a fundamental problem. Now, like on some GPUs, there are it may be the case that it's slightly faster to load a 16-byte aligned block, but it's not like a fundamental limitation that they just can't do that. So a lot of this is, I think, mostly just a driver limitation where the driver compiles the shader and it expects certain rules and then generates certain instructions for the GPU. It's not like GPUs can't do this. And this is why we are seeing these extensions supported on all sorts of GPUs. I'm not sure what scalar block layout support is like. Well, we can check that out. But I'm assuming that there are some desktop vendors that support it by now. Yeah, so like 41% of devices in the database support it, which is pretty good. Looks like AMD and NVIDIA cards do. I don't know if Intel has support for this yet. It doesn't look like they do. But Intel usually is a bit behind on Vulkan, on new Vulkan features. I don't think it's like a problem in the sense that Intel GPUs can't support this. I think it's more like Intel driver team hasn't gotten around to supporting this yet. So not a fundamental problem. But yeah, no, like there's no magical layout that the driver performs. This gets harder and harder as these modern APIs appear, because there's not a dedicated point where you can say, well, I know that the data that was uploaded from the CPU will be used in this shader, so I will just mangle this data so that that shader can be faster. Like, this gets harder and harder. So, all right, so that was the kind of moving closer to the C section of the Vulkan 1.2 spec. So again, reminder, like most of these, right, with the exception of the uniform buffer standard layout, which honestly isn't as interesting, are optional, which means that it's not quite the case that you can use all of this in your production 1.2 renderer yet. But hopefully this will be the case one day. So let me move that out of the way. And let's talk about more things. So one thing that's kind of in the same vein but slightly different that I should touch on is the atomic in 64 stuff. So it's kind of similar, but I didn't want to talk about this in the same, like in quite the same vein, because there is like actually use cases that require this and don't really work without this too well. So this extension is about atomic instructions in the shaders. And it's about the fact that right now, if you want to use an atomic operation like an atomic max or something like this, so let's say you have a compute shader, and then in your, like you're trying to perform a parallel reduction, so you have like a block of 100 or more, I don't know, floats, and you are trying to find minimum of them. So you can do this in compute shader by using these atomic instructions. The problem is all of them work with 32-bit types only. And so this is similar, except that instead of going down in the type width, instead of saying we want to support 8 and 16-bit types, it's going up. It's saying, well, there's a 64-bit integer type. I don't think a 64-bit integer type is supported for storage and like arithmetic perspective. So this is one other kind of place of the specification in the current computing world where we could move closer to C. But so there are some interesting tricks that are hard to do if you don't have a 64-bit atomic. One example that I thought of that is kind of occasionally talked about that should be easier with this extension is this. So let's say you have a shader, and in this shader you have a lot of float values, and let's say these float values represent depth, or like Z, right? And so you want to find the minimum, the pixel, the pixel with the minimum depth, right? So with the atomic operations, you can easily do this by using the atomic minimum on the Z value. And the reason why this might be useful is if you have a bunch of pixels, and then you say, well, a bunch of transparent pixels, and then you say, well, I want to kind of find the closest transparent pixel to the camera, or like the farthest one, so that they can process it first or last or whatever. So, and you can do this, it's fine. Here's the question. So what if instead of finding the Z value of the closest pixel, you actually wanted to find the color value of the closest pixel? And the answer is it's hard because like to find the minimum Z, you can just say atomic minimum of Z, right? But to find the color of the pixel that has the minimum Z, you have to identify this pixel, and it's hard to do with atomic instructions. There is this cool trick that I have seen used in some independent transparency order independent transparency implementations, where you say, well, let's build a 64-bit number that will be structured like this. The high bits of this number, the high 32 bits of this number, will store the Z value, and the low bits of this number will store the color, or maybe the index, or some other entity. So let's say this is, let's say this is RGBA packed into 32 bits, right, with 8 bit per channel. If you perform the minimum operation on these values, on these 64-bit integer values, well, what actually will happen is the Z value of the number will be responsible for the actual result of the comparison unless Z is equal, right? Because if you have a number that's like 0x0001 and then something else, and you have numbers like 0 753 something else, like you don't need to look at the lower bits, the second number is larger, right? And so if you perform minimum on these guys, what happens is the resulting number has both the z and the color of the pixel with the minimum z. Except if z's are equal, in which case it has the minimum color out of the pair, which is a weird tie-breaking rule, but who cares? And so this requires 64-bit integer atomics, and they weren't supported before, and now they are, right? So cool. Again, this is an optional feature, so whether you can or can't use this for some of your rendering algorithms depends on the hardware, right? We can check. I'm pretty sure all AMD devices support this. I don't know about NVIDIA. So let's see, KHR shader atomic and 64. So no, yeah, AMD and NVIDIA. And again, no Intel. I don't know whether Intel can support this. I'm hoping they can, maybe not, who knows. Like this is why some of these extensions are optional, right? So AMD and NVIDIA clearly have hardware capability to implement this specific one, but it could be that Intel doesn't. And so if Intel doesn't, if this was a required feature in 1.2, then all current Intel GPUs, or some large portion of them, would be forced to not be compliant with 1.2, which is not great, because what if you want to use other features of 1.2, right? But the hardware can't say, I support 1.2. So this is why some features are optional. My understanding is that the features that are required are features that basically every implementation of 1.1 can support, and so it can be bumped up to 1.2. So this, I think, is the logic. All right, so we talked about types. Let me look at chat, and then we will move on. All right, let's move on. Stream status is poor again, but I'm assuming it's working fine. This time I disabled VPN, and Google speed test said that it's awesome. It's like, I forgot, 40 megabits upload, but clearly it's not 40 megabits upload anymore, but who cares? I blame Comcast. Anyway, let's proceed. Wait. So, talked about this, kind of also related to extended type support, just a bit different. So let's talk about, there's 3 extensions on the list that relate to depth stencil. So let's cover them briefly, because 2 of them are pretty boring and 1 of them is really exciting. So let's cover the boring instructions first. So there's this why am I doing this here? So there's this guy, separate depth stencil layouts, and then there's also this guy, which is not required for some reason, but it actually might be. Maybe I missed it in the required spec. Anyway, what are these extensions talking about? So again, this is the interesting kind of excurse, like interesting trip into the past with respect to the evolution of the graphics. So it has been the case for a number of years back in the day, that you thought of depth and stencil as a single buffer. And the reason why you thought of depth and stencil as a single buffer is because it was. So there's this commonly used format, which is D24S8, which literally means there's 24 bits of depth and 8 bits of stencil, and literally in the hardware at some point in time, there was a 32-bit value, and it had 8 bits for stencil, and it had 24 bits for depth, and that's what it was. Naturally, if you want to read from this buffer, or if you want to write to this buffer, or if you want to clear this buffer, you kind of think of this buffer as a single entity, right? However, of course, this kind of world didn't really survive through this day. It's not the case that every architecture does things like this. So why not? So the first problem with this kind of thinking is that, well, so let's say you had a pass that disabled depth checks and activated stencil checks. So like you have some stencil operation that says I will only want to render this pixel if the stencil value is 1. Or maybe you want to pass that only write stencil data. For example, I will write 1 for every pixel that I'm rendering. And these are actually quite common. Like if you think of some common stencil-based optimizations, for example, you have a deferred renderer and you want to render a volume that represents your light, and you want to mark bits that it touches with 1 and stencil, so that then you can render some other volume and actually shade these pixels. Or like there are cases where you want to render the sky and you want to render the sky and mark the pixels of the sky in stencil so that some later pass doesn't have to read them, or like things like that. And so, well, you could just write these 8-bit values and ignore the 24-bit values, but this results in a really, really poor write pattern, right? So it's like for every 32-bit value in memory, consecutive, you want to write this guy and ignore everything else. This is a terrible pattern of writing to memory. This might mean that your bandwidth of writing to memory is like 4 times smaller than what it could have been if these bytes were sequential in memory. So that's not great. However, also the other problem is, turns out 24 bits for depth isn't good enough. Turns out the good format for depth is the 32-bit format, where instead of using a fixed point, you use a floating point value. I really highly recommend, if you have a renderer that deals with large distances and you haven't migrated yet to first 32-bit floating point, second, crucially, it's called reverse or inverse or inverted or whatever Z. If you haven't done this, you should do this. This is like the single best thing you can do to reduce Z fighting, to kind of improve depth precision. With this format, it stops mattering too much what your far plane is, what your near plane is. It's like awesome. You should do this. So, but the problem is if you have a 32-bit depth value and you also need a stencil value, what do you do? The original motivation for the 24/8 format is that some writes, some GPUs had restrictions around we can only write to 4-byte aligned blocks. We can't write to like 5-byte blocks, right? And so if you have 4 bytes that you want to spend for depth and 1 for stencil, what do you do? There's this really weird format that I won't go into the details too much, but there's this format D32F, I think in DX11 probably, yeah, S8X24. And literally what this means is there's 8 bytes, and then in this 8 bytes there's 4 bytes of depth and 1 byte of stencil, and then 3 bytes of garbage. Not all GPUs implement this like that, but like whatever. So point is, it's kind of weird to think of depth and stencil as being one thing. It's kind of 2 separate buffers. And if you look at Metal, for example, Metal actually says, well, no, there is a depth texture or image or whatever, and there's a stencil image, and they are separate. Of course, when Metal was ported to Mac, I think they had to reintroduce pack depth stencil because there is some hardware on Mac that cares. But this is a historical artifact. Like, at some point in the future, I would expect that we stop talking about depth and stencil as being part of one texture. I don't know when this will happen, but at some point it will. So today, there is some hardware, such as... I will not talk, it's hard for me to... Like, I'll have to think which kind of details of hardware are public domain, which parts aren't. So there's some hardware that uses separate depth stencil, and there's some hardware that doesn't. So this brings us to the problem, which is that what if you want to do operations on just one half of this combined like depth stencil buffer without touching the other half? And in fact, the DX12 API, while it doesn't have separate depth and stencil buffers, it does have separation between them in the sense that if you want to say, I want to read the depth value in the shader. What you have to do is you have to take the texture and say, I want to transition the texture to be readable in the shader. But in DX12, you only do this for the depth portion if you only need the depth portion. And so this is what these extensions do, the separate depth stencil layouts and usage. They allow you in Vulkan to reason about depth and stencil independently. When you talk about the layout, so like can I read this, is the depth or stencils in the format that is readable in the shader or writable from a rasterization unit or something like this. And separate stencil usage is similar. It says you can create a texture with separate stencil usage that says, well, I will sometimes want to read depth from the shader, but I will never want to read stencil or something like this. And the reason why this might be useful is that some hardware may look at this and say, well, cool, you will never read stencil in the shader, so instead of putting this in the memory in a format that is readable by the shader, I will put this into memory in some other proprietary format that is more efficient, more compact, like who knows. And then it's never a problem because the shader never needs to read this, even if the shader does need to read the depth portion. So to my knowledge, these are mostly important for projects like DXVK, where there is a DX12 API that says you can work with depth and stencil separately as part of the same texture. And when you translate this to Vulkan, which is important if you want to play DX12 games on Linux, right? You really want this extension so that your translation is like reasonably fast. So that's the stencil bits. And now let's talk about the depth bits, because the depth bit has very practical. So this basically has some practical value in the desktop space. The new depth extension has a lot of practical value in the mobile space. Oops, hold on. Oh, and I will. What the hell? Okay. I stopped being able to move things around in this tool. What the hell? Okay. All right, I guess we're just gonna delete this. I don't know. It's all very odd. Oh, okay. I can move this with a finger, just not with a. All right, whatever. Let me look at chat. Reverse Z is amazing. Yes, reverse Z is amazing. Everybody should do this. Yeah. So when Apple shipped Metal on Mac, right? The problem with Apple is on desktop side they switched the preferred hardware vendor. It used to be that all Macs were NVIDIA and Intel integrated, or just Intel integrated, and now they are AMD and Intel. And because of this switch, there's features of the API that have to cover the hardware capability of kind of both, and restrictions, most importantly, right, of both AMD and NVIDIA. Which is unfortunate, but I mean, that's kind of what it is. There are no new Macs with NVIDIA hardware, and they haven't been for a while, but I think you can. My impression is that you can buy a MacBook today, and then you can buy an external GPU enclosure connected through Thunderbolt, and in that enclosure you might be able to insert like a more powerful NVIDIA card, and maybe it will work, subject to driver availability and stuff, who knows. Anyway, so let's talk about, hey, all right, let's talk about depth stencil resolve. So we talked about the depth and stencil and the depth stencil separation. Now let's talk about multisample anti-aliasing. So brief kind of refresher, right? The way multisample anti-aliasing works is, let's say you have 4x MSA, and the GPU renders an image, and in each pixel of this image, it renders 4 samples, and usually there is a rotated grid for 4x, so it's like something like this. these are the locations of the pixels that are, or samples that are rasterized. And so this is one pixel, right? And each square inside the pixel is called a sample. And then for each sample, there is a unique color value, and there is a unique depth value, and there is a unique stencil value. But when you render into this thing, the shader usually gets run once per pixel, and then the value gets propagated to individual samples. And after the rendering is done, there is a process that's called resolve that just merges, like averages all of the color values, picks the, who knows what it does with depth. This is actually what we're going to talk about. And so basically it results in just one average pixel value. And this is what makes it, roughly speaking, this is what makes the edges look nicer under MSA. So the question is, how does this resolve operation work in Vulkan? And the answer is there is two options for this. One is what's called CMD resolve image. There's actually three options. Then there's another one which is, let's call it resolve attachment. And then the final one is, let's call it shade resolve. So shade resolve means you write a shader that reads the MSA texture directly, so it has access to all 4 samples. It performs an arbitrary computation on these 4 samples, it doesn't matter, and then it writes the result out. CMD resolve image means that you just have a command that does this transition in your command buffer. Resolve attachment means that when you render a render pass, when you begin a render pass, instead of saying, I want to render to this MSA texture, you say, I want to render to this MSA texture, and then resolve it to the one, like to the non-MSA texture where there's just one value for each pixel. And so on desktop hardware, on some desktop hardware, all 3 of these options can be reasonably efficient. On mobile hardware, there is exactly, on mobile hardware things are complicated. On mobile hardware, CMD resolve image is a terrible idea. Like never use this on mobile. Prefer resolve attachment. And avoid, I would say, shade resolve. The reason why I say avoid is, in theory, there are ways to implement shade resolve on mobile that are, in theory, fast. In practice, based on what I heard from last year, like, drivers didn't really seem to work the way that you would expect them to work in this area. But so, the dominant way to work with MSA on mobile is resolve attachment. So why is this much better on mobile? Mobile architectures work mobile architectures are tilers. So what this means is there is a large tile of pixels, and then there is a bunch of triangles here. Some triangles are contained inside the tile. Some triangles are actually crossing the tile boundary, and so they are part of multiple tiles. And so when you submit a mesh in mobile, when you submit a scene in mobile, I should say, with a bunch of draw calls, so this is a render pass, right? What happens is, on many mobile architectures, is the screen is split in tiles. Within each tile, the rasterizer renders all of the triangles to this tile, runs all of the pixel shader work, etc., 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 and then writes the tile to memory. And so the thing that a lot of mobile hardware can do is that the tiler works with MSA. So you rasterize all of these triangles into the buffer, into the on-chip memory, which hosts the tile depth and color, etc., with MSA, which is 4 times larger, 4 times more data, right, than the non-MSA result. But then, instead of writing the thing to memory, there is a resolve operation that goes from the on-chip tile memory directly to like RAM. This means that instead of writing the MSA buffer to memory, right, you write the MSA buffer to the on-chip memory that is typically much smaller, it's like hundreds of kilobytes or something like this. But it's much faster, like much faster. And then the resolve operation does all of the math on the data from the on-chip memory and then just writes 1 pixel to RAM. So this is awesome. The problem is this only works for color. So then the question is, on mobile, what if you have an MSA renderer and then you want to take the depth value and then you want to run some post effect or something like this that works with that depth value? And the answer is you don't do that, because if you were to do this, it would be really slow. And this is what this extension solves. This extension can now do the resolve not just for color, but for depth values efficiently without going through the memory. And I forget what specific like operations it can do, if it can just pick the corner or if it can do min-max. I'm not really sure, I don't remember. Let's look at this. I think this guy, yeah. So there's a bunch of options when you resolve depth. You can sample just one of the values in your like 4x4 or 2x2 kind of pixel and then return that. This is fine for some effects. You can average. I don't know if the average works for depth. The average is usually not a great idea for depth, but again, in some cases it's fine. And you can do min and max. Min and max are great for depth because this means either the closest of the 4 pixels or the farthest of the 4 pixels. And depending on the effects that you want to run, some of these may be more or less appropriate than the other. So this is great. This makes depth-based effects much more practical on mobile if you use MSA. For example, in Roblox, we run MSA on many mobile phones, not all of them, and we disable every single thing that ever wants to read depth. Not necessarily because by itself it's too slow to do that, but because the resolve is so expensive that we just say, well, we shouldn't do this ever. And so with this extension, we actually could run some of the depth-based post-processing on higher-end phones at much less of a cost than what it could be today. And one other thing to mention is that on mobile, actually, you do want to use MSA in general, because MSA with this fast resolve costs you very little. Because most of the work is done on chip and the fast style memory, and so you get a lot of quality improvements for really very little cost. So that is that. Let me get rid of that. Okay. All right. Let's look at chat. There were driver issues as in no drivers for newer NVIDIA GPUs and Macs, something like this. Yeah, probably. Maybe somebody repackaged NVIDIA drivers, which is what people do. Stuck on GPU family. Is reverse Z used to get higher precision? Yeah. Let me Google. There's like a bunch of articles on this. Basically, you just Google reverse Z and then you follow the link trail, and then they will tell you kind of why this is nice. OpenGL is a terrible API because in OpenGL it's really hard to use reverse Z up until OpenGL like 4.5 or something like this, which is available on desktop hardware but on Windows, but like not on Mac and not on mobile anywhere. So in OpenGL, you can't really do this because OpenGL made the wrong choice when specifying the... It's like... It's a terrible story. I will not go into the details. But if you don't use OpenGL, you are fine and you should use reverse Z. Does resolve attachment always goes to RAM, or is it not guaranteed that you get a flush? Any chance resolve to happen still on chip? Well, so I was assuming that you just have a single render pass, and if you have a single render pass, then it goes straight to RAM. In theory, right, you could create a sequence of render passes. So you have a sequence of subpasses. So you have a render pass and you have two subpasses in it. So one of them like renders MSA, right, content, and then there's this resolve thing, which is part of the subpass, and then it goes into the resolved thing, and then there is some maybe shader post-processing operation that reads that, and that's part of your render pass, right? So like this is a subpass and this is a subpass. And in theory, the driver could make it so that the resolve actually goes to on-chip memory, just to a different destination, and then the rest happens like on-chip as well. So to my knowledge, no driver can do this today, but in theory this is possible, right? So like you could implement a Vulkan driver that does this. You might even be able to implement a Vulkan driver on some of the existing hardware that does this. I'm not sure, but to my knowledge, drivers don't do this right now. I could be wrong though. We don't really use subpasses because separate discussion. So, but yeah, in theory you could do this. In practice, it usually goes to on-chip, to RAM. Hold on. Hey, my Microsoft Whiteboard connection has issues. Hopefully they will recover soon. Maybe they won't. Hello. So what you see on screen is not what I see on my other screen. Oh, great. What? Okay. So this is what network synchronization issues look like. I'm not sure. Oh, I guess I can delete this on this screen. If I can select this somehow. All right, hold on. Let me repair the network synchronization issues by hand. Can I like... Is that... Aha. Oops. Okay. Okay. Network desync fixed. All right. Let's talk about other things from this list. What should we start with? I'm saving some of the juicier. We can talk about the juicier bits. Let's talk about a few really small things just to kind of get them out of the way. So, like really tiny things that just will say like 2 words or 3 words. Actually, there's not that many things like this. Oh, yeah. So, okay, whatever. Let's just go through the list. So, I will cover buffer device address a bit later because it fits a theme with one other extension. Let's talk about some other things that are kind of small. So create render pass 2. This is really straightforward. This is needed to... So in Vulkan, every time you have a command that needs to be extended, let me try to go to the actual code that we have. Begin... Oh, no, not here. So if you have a command... So this guy has it, but like, yeah, so you have a command begin render pass, and then this command references a struct, and the struct has these 2 fields. And these 2 fields are important because, well, okay, this field is important, this field is less important. But this field is really important in that specific struct because this is how you can specify extra information to the driver that comes with extensions. So if render passes have some extension, then you would set p next to the next structure in a chain that has the extension information. And so my recollection for the for the create render pass 2 is that this is mostly a cleanup extension where in some function, I forget which one, is it maybe create render pass? There was some function where there was no pnext pointer, and I don't remember which one it was. We can look at the extension spec and like it will tell us. Oh dear God, we probably don't want to read the extension. Okay. Right, yes. So the point of this extension is this. If you have render pass and you want to specify an extension for the render pass, the only place in Vulkan 1.0 that you can do this is on the create info struct. So for example, let's say you have an extension that says for each attachment, I want to provide extra values. Instead of having pnext pointers like here for each attachment description, you have just a single pointer here. So you have to have a struct that has an array of attachment structs in the extension and then link it to this guy. And I think the second version of the render path creation puts pnext pointers like everywhere in all of these structures, so that it's easier to extend them. It's not really consequential. I think it also merges some multi-view stuff into the baseline. But point being, this is a software cleanup thing to make it easier to extend Vulkan in the future. Maybe Imageless frame buffer relies on this, maybe not. Like, not very interesting, honestly, to talk about. Draw indirect count. So draw indirect count is a great extension. We actually used it in Niagara like a year plus ago. What it does is when you have an indirect draw, meaning you have a draw call that uses an array of structures, an array of commands. Where each command has things like how many triangles to draw, so count, like offset, and some other things. You also have to specify the size of the array, right? Unfortunately, and we use this in Niagara because we have a GPU-based renderer that calls a lot of things and then renders them, but it doesn't know on the CPU what exactly to render. And so the size of the array in Vulkan 1.0 was a value that the CPU had to pass to the GPU. But what you really want is to actually have this value come from GPU memory, because again, in Niagara, we have a compute shader that does culling, and so it takes a lot of meshes, and then it outputs an array of commands that correspond to visible meshes. But then it also outputs the size, right? And so draw indirect count is an extension that allows you to read this count from memory. We used an extension for this in Niagara, and now this extension is part of the Vulkan 1.2. Again, optional, so you have to enable this, you have to check if it's supported, but hey, at least it's there. And I think DX12 supports this natively, so again, it's like slightly helpful for DX12. So this extension is great. It's just very small because it's like one function, and it's literally changing the fact that the function takes an integer to a function that takes like a buffer where this integer is stored. That's it. Really simple. We use this great extension, just small. Driver properties. If you let me look at our code, and I will. So if you create a Vulkan device, you have to say which physical device, which GPU to create it for. And you can look at, I think in this guy, yeah. You can look at a struct in Vulkan 1.0 that contains information about this device. And in addition to the device information, it also has the driver information. So specifically, it has the driver version. And so the notion here used to be that you can look at this driver version and identify the specific driver. And this is useful in a number of ways. One is when you talk to a graphics driver vendor and you're like, hey, I think I have a bug. They will ask you what software and hardware you're running. And so what driver version are you running? Well, I'm running driver version 1.x, right? So this is the version. Or it may be tempting to say, well, there is this bug and I have found this bug on production devices, so I want to work around this bug. But the workaround is expensive or fragile or whatever, so I want to only work around this bug on devices that have this bug. So it's tempting to say, well, on like this vendor, this bug happens on driver version X, but it's fixed in driver version Y, so if driver version is less than Y, I'm going to apply the workaround. All right, here's the problem. And also one other thing. On some, it's tempting to think that there is a one-to-one correspondence between the vendor ID, which is the PCI ID of your GPU, like NVIDIA, AMD, etc., and the company that makes the driver. But actually, this is not true. There are two AMD drivers on Linux. One is made by AMD, one is made by the community, basically. And there's two drivers for NVIDIA. One is made by NVIDIA, which is a proprietary binary driver, and the other one is made by the community of reverse engineers. It's called Novo. So like this means actually you don't even know which driver's version it is you're looking at. But the problem also with driver version is that it so happens somehow that so there's two issues with this in practice. One is there are some vendors, I will not name them, but there are some vendors who say, well, instead of versioning the driver with like an integer, we will just put a hash of some binary blob structure, maybe like the driver executable, into that thing. And so instead of seeing like 1.0.4 here, you see literally like X, BCT, like BCF 78123, I don't know, right? And the issue is you talk to the driver vendor and they ask you what driver it is do you have, and you're like, well, my driver version is BCF 78123, and they're like, what? And the other issue is that it's tempting to say, well, there's driver version 1.04 and one driver version 1.10, and so if the bug was fixed in 1.10, it must still happen in 1.04 and vice versa. But it's not actually true, because there is complicated delivery problems with this. For example, on mobile, the GPU manufacturer like ARM doesn't ship drivers. The entity that ships drivers is the company that manufactures your phone, like Samsung. And so what exactly Samsung does with drivers, nobody knows. And so this is why this idea kind of didn't pan out in practice, like the driver version isn't actually useful. So what is useful? Well, who knows? But here's the thing that we're gonna try with this extension. And I know what it does, but it's easier to explain if there's a struct in front of me, so we'll go to this guy. So there's two problems. Oh, and actually, oops, wait. Here you see this kind of conflation that I was talking about. There is an AMD proprietary and AMD open source driver. There's an NVIDIA, this guy doesn't have Novo, so I'm not sure what it masquerades as, but there's several NVIDIA drivers. Oh, actually, sorry. These are two, okay, it's even worse, right? This is the open source driver that's made by the community for AMD. This is the new AMD open source driver, and this is the old one. I didn't even know the old one supported Vulkan, but I guess it does. Whatever. There's like several Intel drivers, stuff like that. So if you look at the struct, and if I can find this struct, here's what the struct tells you. So it tells you the driver ID, which is like, okay, we know your GPU is NVIDIA, but who actually made the driver for it, right? These are just strings, but these strings encode information that the vendor of the driver will understand. So if the driver info says, well, it's a driver 1.0 built from branch master with like patches X and Y, with like git sha this, then you don't know what this means, but you can send this information to the vendor and then be like, oh yeah, we know what this means, right? So that is useful for this. And then there's the conformance version. So here's the idea of the conformance version. And we haven't used this in practice, so who knows how well this works, but here's the thought. And conformance version, I think, is just a semver version, major, minor, some minor patch. So what is this version referring to? Well, so there is the repository called vk-glcts, but basically we are interested in the vk part, which is the conformance test suite. So what this does is it hosts a set of tests that you can run on a Vulkan implementation, and they will check whether this Vulkan implementation is actually compliant, if it actually implements Vulkan, right? So it will do things like, hey, let me like draw this thing with this shader and check that the shader produced the correct result. Let me call this API with this value being 1, and let's check that your driver actually respects this value being 1 if it's encoded in the spec. And of course, this is it's like, how do you test a driver? There's so much code there, and there's so many different drivers. So you can write so many tests, but you can't cover the entire driver with them, right? And so these tests are not comprehensive, but they're the best we have. And so I filed many issues on this repository. Let's see how many. 11, and all of them are closed, which is great. Thank you, people who closed the issues. people who write tests. But here's the process. So let's say we find a bug, and I encourage people to do the same. Let's say we find a bug in the Vulkan implementation, so in the driver. And we're pretty convinced it's not our bug, it's like the driver bug, right? So if there is a conformance test that has this exact code running there, then it should follow that this test failed on this implementation. And so if there is no test in the conformance test suite, then you file an issue to ask to add this to the conformance test suite. And when the issue is added, this makes sure that when the drivers are certified with that version of the conformance testing suite, that issue shouldn't happen ever again, right? And so in theory, you can use this version to then toggle your workarounds. So the thought is, okay, we found an issue X. Either there was a test for this in the conformance testing suite, or we asked to add it and it was added. And so the first version of the conformance test suite that has this test is 1.7.1. If the driver was certified on the version that is less than that, then we don't know. It might work, it might not work, who knows. But if the driver was certified with that version later, it should follow that this bug shouldn't happen. And so it should be free to use this. It should be, we should feel free to use this feature, right? So that's kind of the thought. Who knows if this works in practice? I haven't checked. Like, the drivers should expose this extension. They should honor the version number. Like, who knows how this works in practice? But that's the best idea that people came up with for now. Maybe Nova only supports OpenGL. I do not know. I don't really use Linux. All right, so we talked about the driver properties. And so a lot of these issues may seem kind of weird, but this is what software looks like at scale. Like, it's fine to just develop like a library or a piece of hardware or whatever in isolation, and you control everything and everything is simple. But then, oops, wait, hold on. But then you actually ship your hardware and software to actual users in actual devices, and then you discover, well, actually things are really complicated. All right. Image format list. Okay, that's a really simple extension. Very briefly. So we are like halfway through, but there's a couple of small things that we will just knock out of the park like right now, and then there's going to be a couple of more meaty things and one really meaty thing, two actually meaty things and one kind of medium-sized thing to talk about. Oh, maybe more. Oh my god, there's a bunch of stuff left. Oh well, all right. So let's go through that. So image format list, very briefly, it's not terribly interesting, but the idea is as follows. So in Vulkan, you can create an image of format X. Let's say like RGB8, RGBA8, whatever. And then you can create a view of this image with some other format like RGB8, like sRGB or something. Or there's like examples where you create an image that is 32 float format, and then you create a view of this image which is 32 integer format. And I think the spec by default says you can't do this, but you can create an image with something called mutable format. Mutable format. That says I will create views for this image that have a format that is different from the base format. Mutable something. Oh, this is the wrong, hold on. This is the right spec. Mutable. Yeah. Oh, this is great because this is exactly, okay. Let me. Yeah. So whenever you want to reinterpret the formats, you have to create an image with this format. But so the problem is when you say I want to create an image with a mutable format, it's very, let me get back to the quote. yeah. So it's very lax. Like you're not saying I will create an image view of these other formats. You're just saying I can create an image view for this image of any other format, regardless of what that format might be. And on some hardware, on some images, it's actually not very efficient to do this, in the sense that some types of format conversions in hardware are free because the layout in memory is the same, so you just create a different descriptor for the same image and you're good. But on some hardware, it might be the case that the floating point image and an integer image are stored differently. And so if you create a floating point image and you say, well, I might want to reinterpret this to something else later, the thing might assume, well, you want to reinterpret this to the format that is expensive to reinterpret to. And because of this, we are going to pick an inefficient internal representation. And this actually isn't the case oftentimes. I think one core example of this is it's really, really useful in graphics to be able to interchange between these two formats, like RGB8 and RGB8 sRGB. There's no memory differences here, it's just 4 bytes with RGB data, RGBA data. But when you read or write to the sRGB image, there's extra conversions that are going on between sRGB and linear. And in some shaders, you may want to read the raw bytes of your RGBA data, and in some shaders you may want to do the sRGB to linear conversion. And so it's really, really tempting to create like every single image with this mutable format, but you may run into performance penalties on some hardware. And so what the image format list extension does is that instead of saying, I will create an image that might morph its format through a view later, I will create an image that might form its form through a view later. And by the way, here's the list of formats that I promise to only kind of limit myself to when creating the views. And so you could create an image that says, well, here's the format list of the views that it could be used with, and it's RGB8 and RGB8 sRGB. And then the driver doesn't assume that, for example, maybe you want to reinterpret to R32F, which is like the same amount of bytes, but might be a different structure. And that can make, basically that can result in you being able to interpret between sRGB and non-sRGB formats at no cost. On some hardware, this is not an issue. Like on some hardware, there's no extra cost for the mutable image format, but on some hardware there is. So now you can use this extension and basically remove this cost from some hardware. And this is a nice extension because for some extensions, it's hard to handle the case where they are not supported. Or this feature, I should say. I keep referring to this as extensions. This is because they were extensions originally, but now they're part of 1.2 spec, right? So they are in core. But so it's easy to handle the case where this specific feature is present or not. Because if this feature is absent, you can choose to just create the images with mutable format and just not specify the format list. And it might be slower on some hardware, but this hardware doesn't implement this extension, so I guess it should suffer, right? Some other features are really hard to handle the absence of, because it's like your core rendering algorithm relies on like Bindless, and what are you gonna do if it's absent, like write a second renderer? I mean, you could, but it's a lot of work. All right, so I want to talk about Imageless frame buffer separately. Mirror clamp to edge, really boring feature. There's a new sampling mode now where instead of clamping to edge, so instead of like 0 to 1 UV space, and if you sample like 1.5 or something, it clamps to 1. Mirror clamp to edge mirrors once, so I forget which direction it is. I suspect it's like -1, 0, 1, and then if it's less than -1 or greater than 1, it clamps to -1 or 1. But if it's like -0.5, then it mirrors your image. So if you had like something like this, then you get like something like this. I think the only purpose of this is DX12 has this, so if you're writing DXVK and somehow some game uses this for whatever reason, if you don't have this extension, it's going to be really painful because you have to emulate this in the shader, and with this you can just use this. I don't really know why you would use this on your own, but hey. All right. So what else? Shader float controls. I don't really want to talk too much about because it deals with some esoteric, like if in your shader you want to specify how you want to handle denormals or how you want to handle infinity and nan or like whatever, you can control this now. I don't really want to talk about this because there's other more interesting things in my mind to talk about. So it's like mildly useful if you really care what exactly happens on your GPU with floating point data, and if you do, you should probably read the spec, but it's not super interesting otherwise. Spear v14 is also not really interesting. I might talk about the both Spear V versions separately later, but maybe not, so I'm not gonna cover this right now. Timelapse semaphores we'll talk about separately. Vulkan memory model. I don't want to talk about this either because honestly I don't understand this. Or the notion is, if you read the spec, there is like some amount of text that tries to specify what exactly happens when you access memory, when you write to memory, when you read from memory, etc., etc. But it didn't have a formal memory model where there is exact, precise specification for the entire flow of like what happens when you use a memory operation. And I don't. So my understanding is it was a lot of work to standardize the memory model, but I don't know that it's actually really useful, except for when you have a question like, I'm doing this thing and this driver doesn't work, should it work? Or am I doing something illegal? It's easier to answer these questions if you have a formal specification of the memory model, but I think it doesn't actually serve a practical purpose for like people who use Vulkan. So descriptor indexing we'll talk about later. Let's cover these other three things. These are the two things, and then the third thing, and then we'll talk about the three actually meatier topics left. Oh my god, there's also subgroup broadcast dynamic ID, which some people like. Alright, so host query reset. Actually, I will not talk about this too much. This is just if you have a buffer with query data like occlusion query or timestamp or something like this, there's an operation on it called reset, which makes the queries available for later use. And before this extension, before Vulkan 1.2 in core, you could only reset a query pool from a GPU. So you could say, here's a command to reset the query, but you couldn't on the CPU say, I just want to reset it right now. And there are reasons why this is a bit painful. We actually ran into the lack of the host query reset at Roblox like last week, because we were adjusting some profiling code to work better on mobile devices, and we had to reset the pool, and there was no like common buffer already available to that code that wanted to reset the pool, but the code could have reset the pool on the CPU. It was fine, it's just it wasn't an option. Now it's an option. My understanding is if you are, again, writing DXVK, then DX12 provides this functionality, so you really want this functionality because otherwise DXVK translation is really painful. Filter min max, awesome extension. We use this in Niagara. So you can watch the streams where we do occlusion culling. The idea of the extension is you have a pixel, you have a texture, sorry, and you have a sample operation inside this texture. And traditionally, there's a few filtering operations available, specifically linear or like bilinear filtering and point filtering. Point means I will take the pixel that the point of sample is in, like the bottom right, and return that value. Bilinear means I will take the three neighbors, so like the actual 2x2 quadrant, and interpolate between all four positions, values. Min and max just mean I will take the minimum 4 values or the maximum 4 values. And the reason why this might be really useful is when you work with depth, which is what we did with occlusion. So when we worked with occlusion, we use this for two reasons. One is when you want to do a mip-map generation of this texture, it's convenient. Like what you want to do is you want to create a new texture where for each 4 pixels there is a new pixel that's the minimum or maximum of these, and you could sample these 4 pixels and in the shader just apply a minimum operation of them, but it's like slightly faster and slightly more convenient to do this with one sample. But the more important use is, so we actually use this in in a few shaders. So this is the use that I was talking about. Like we just sample the corner, like the corner of 4 pixels, and we rely on the sampler setup to do the min reduction. So it just returns one value, which is the minimum of 4. But the more important use is in culling, where we use the exact same code. And there, the notion is, it's kind of similar. It's like, hey, there is an object, and the object has a certain footprint. Let's take the center of this object, and let's sample the pyramid of the depth values at the right MIP level. And to do occlusion culling conservatively, we have to ask the question, is the object behind either one of these 4 kind of pixels? And for this, you have to do comparisons to 4 depth values, or you can return the minimum of them or like the maximum of them, whichever way it goes, and then perform a comparison once. And it's the same thing, it's just that when you do culling, performance is more important because you have a lot of objects that sample from various locations in the texture. And so this is much, much easier to do when you have this min-max thing. So it's now available, it is not required, so you have to check for it being supported. Also, it's a feature in DirectX 12, so again, if you're working on DXVK, there are many games that use this feature for similar reasons when they use DirectX 12, so it's going to be harder for you to like make a Vulkan implementation of this game in a straightforward way. All right, we're getting close to like scary parts, big scary parts. But let's first talk about one thing that I am passionate about, which is small. Yeah, you can do it in render pass. That is true. So I'll answer the DX12 stuff and the vendor stuff a bit later. Yeah. Oh, there's also Imageless frame-buffer that I wanted to talk about. Oh, yeah, okay, that's fine. So, viewport index layer, what is this? So when DX10 came around, DX10 had this amazing feature called geometry shaders. And the amazing feature called geometry shaders was fraught with peril, but so tempting to use. So there are some examples of the geometry shaders being used to actually amplify geometry, like here's a triangle and just render like 5 triangles instead of that for various reasons. But there have been a couple of examples of geometry shaders being advertised for actually improving performance. Spoiler alert, it didn't work. But the thought process was like this. So here's one canonical case. Imagine a cube map which has 6 faces, and I'm gonna only draw 3. Well, okay, fine. Here's the cube map. And imagine there's an object that you're rendering to this cube map. And so the traditional implementation is you have 6 passes, and in each pass you bind 1 face, and then you set up the camera so that it's like a 90-degree angle, and you render things to that camera, and then basically your entire scene, right? And then you do this again, 6 times. And so the worst case performance impact that you're getting is that you need to render each object 6 times into 6 different views. And so that's a problem from the GPU performance perspective, but it's also a problem from the CPU performance perspective, because 6 times more draw calls is slower, up to 6 times, than like not do that. And so the message was like this. Well, it's very simple. Let's write a geometry shader that takes a triangle, that duplicates it like 6 times, right? and transforms each triangle with like its own transform matrix and stuff. But it's not enough. You transform the triangle into the perspective space of whatever camera you want to render it to, but you also need to say where to write the pixels. And you can do this from a geometry shader, but what you can do from a geometry shader is you can say, well, instead of binding just one 2D texture, I will bind 6 of them as render targets. So specifically, I will bind like a render target array of 6 textures, which happens to be the same as a cube map, more or less, from the API perspective. And then in my geometry shader, I will just, for each triangle that I duplicated, I will say you go to the array index 0, you go to array index 1, etc. There are other uses that are very, very similar to this, where you take a triangle and you kind of broadcast it to a few render targets. There are examples in shadow map generation, where sometimes you want to render an object into multiple shadow cascades at once. There are examples. I actually used geometry shaders with this kind of trick in my 2015, 16 was it, the next generation voxel rendering hackwick project for Roblox, where I had to write a voxelizer, and the way my voxelizer worked, at first at least, is it used geometry shaders to kind of multicast, because if you want to render to a 3D texture, there's no way to do that, but if you reinterpret the 3D texture as this array of render targets, then actually you can do this. But so the problem is geometry shaders are slow. There are reasons why they are slow. They are in general a bad API, in my opinion. Like, hindsight is 2020. When the extent came out, this was, 15 years ago, I was like super excited about geometry shaders, and then I bought 8800 GTX card, or something, yeah, I think GTX, and then I excitedly started trying all of these new features. I had like stencil shadows running in geometry shader and stuff like that. And then I took an SDK sample that did this cube map rendering, and then I benchmarked it, and then performance wasn't actually that good. And then I wrote a good implementation of the same thing without geometry shaders, and it was much faster than either their implementation like with geometry shaders or their implementation without. At which point I'm like, okay, I guess maybe this is a bad idea. But it wasn't probably obvious, maybe, I don't know, to people who were doing this in the first place. So, if geometry shaders are slow and terrible, the question is, can we do this without geometry shaders? And the answer is yes, with this extension. And the way you do this is this. So let's say, and whether you want to do this is up to you. There's cases where it helps, there's cases where it doesn't. But let's say you want to do the exact same thing. You want to take a mesh and render it to 6 faces of the cube maps all at once. Instead of having a geometry shader that duplicates your triangle 6 times, instead you use instancing. So instead of saying draw, you use draw instanced. Oh, and I should mention there are also VR, there are also cases where in VR you might want to use this feature now. So it's like, it has a use. So instead of doing draw, you do draw instance with 6 instances for each mesh. And this results in your geometry being executed like rasterized 6 times. And in the vertex shader, you get what in GL is called GL instance ID, and in other APIs it's called something else. And in Vulkan it's also GL instance ID because reasons. So then what you do in the vertex shader is you transform the vertex with the correct matrix. You have the instance ID, so you can just have an array of 6 matrices bound to a shader, just look up the matrix by index, just transform it. And then from the vertex, you say also I want to render the vertex, but this is not actually what you're saying. You're saying I want to render the triangle to the array index of my render target number like 5. And so the way it works is if you have a triangle, the first vertex, I think, of that triangle determines the, it's either the first vertex determines like the render target that it'll actually go to, or maybe it's like if all three vertices don't agree, the result is undefined. I don't remember what exactly the specification is. And then the hardware rasterizer says, well, with the triangle, here's three vertices, and like here's the index that of the render target that this triangle should go to, and so I'll just send it there. So with this, you can do this multicast without the geometry shader, which means you don't have the problems of the geometry shaders, which is fantastic. So there's many uses of this, as I mentioned, like render to cube map, render to shadow map, VR, voxelization, probably many more that I'm not thinking of right now. This is supported in DX12. This is actually supported in DX11. Let's see if I can find this, because this is kind of hilarious. How do I find this? VPVS feeding geometry shader stage D3D11. It's like some hilariously long caps name. Maybe it's here. Oh yeah, see, so geometry shader overview, and they say here's a use case: single pass rendering to multiple textual cube faces. Don't do that. It's not great. So yeah, DX12 spec says that there should be a leading vertex, but anyway, whatever, it's not actually very important. But point being, so DX12 has this feature, DX11 added this feature in DX11.3 or something like that. Metal has this feature, and now Vulkan has this feature. So it's a great feature. This is honestly like half of the use cases, half of what you might want to use geometry shaders for in practice, or more than half even, I don't know, are covered by this. So it's a fantastic kind of solution to not needing a geometry shader. I think this was originally an AMD extension, and then I guess it became a cross-vendor extension, and then it became part of Vulkan 1.2. But this is optional, right? So this is one of these examples where you actually have to write, hey, stop not selecting things that I wanna, oh my god, wait, no, that's not what I wanted. All right, whatever. So this is one of the cases where if this feature is not supported, it's not as trivial to kind of like just ignore that, like you have to write a fallback path that doesn't use the same shaders, etc., etc. Oops. Also, a lot of the features in SpearV 1.5, I think like half of them, are actually responsible for making this extension work, because for this extension to work, you have to add another possible output value to the vertex shader, which is like the viewport index or the render target index or something like that. All right. So we have 3 topics left. Let me look at questions. Anything VR focused on this new version? I don't think so. So the there was VR features in 1.1. The biggest one was multi-view, and I think render pass 2 that we kind of crossed out already makes using multi-view slightly easier, because you don't have to use like some separate structures for this. But this was the last big thing. I don't think any of this would materially apply to VR, at least nothing that I can think of off the top of my head. So yeah, I don't think so. If you want to write render that's most likely works equally fast on Intel AMD and NVIDIA GPUs, should we avoid extensions, stick to the core? Yeah, so it's a complicated question. So I think the answer is, even if you stick to the core, it's actually a bit of a challenge to write a render that's equally fast on all of them, because there are things that some vendors ask you to do and some vendors ask you to not do. There are some things that are faster on some vendors and slower on others. And there's no like one-size-fits-all advice. I encourage you to look at some recent Vulkan presentations from GDC. Several years ago, AMD and NVIDIA started doing combined, and sometimes Intel, I think, sometimes started doing combined kind of presentations where here's an article about how to make DX12 faster, and instead of like an AMD person telling you all of the things about the AMD architecture, and then you follow them, and then on NVIDIA your render gets slower, they have advice that is specifically marked as, okay, this is cross-platform performance advice. Just do this, things will be better. This advice applies to AMD, this advice applies to NVIDIA, and I think there might be some where there's Intel as well. So it's complicated. I wouldn't say that extensions, by their nature, necessarily make your render faster or slower on different vendors. But so this is kind of part of where the extensions being bundled into core is nice. It's kind of a sign that all vendors looked at this extension and said, this seems like a reasonable idea for our hardware, right? Because there are some extensions that are terrible idea for some hardware, and they weren't, or just like not supportable on some hardware in the next few years, and so they just aren't part of the core, right? So from that perspective, addition to the core does give you like a useful indication, right? It's probably not horribly broken, but there are many features in core that have very different performance characteristics between different vendors. So like, what I think about Turing features adding to DX12 and Vulkan only has them as extensions. They aren't part of DX12 yet. All of the like articles that you see about DX12 getting mesh shaders and stuff like that, I mean, they're all great, they're all true, but like there's no production from what I know. This hasn't been like put into production yet. DXR is live, right? Like ray tracing in general happened on DX12 side faster than it did on Vulkan, but today on Vulkan you can use an NVIDIA extension and it works fine. I think the real question is, so like today on desktop, the only vendor that has mesh shaders and ray tracing in hardware is NVIDIA, right? So like DXR is cross-vendor, but you can use it on AMD and Intel. It's just not going to be very fast. So I think once there is kind of indication of different vendors shipping support for mesh shaders and ray tracing in actual production hardware, then it starts becoming an interesting question, right? Right now, it's still a bit of a research topic as far as I'm concerned. But yeah, so like, I mean, I don't feel bad or good. I think Vulkan has showed an ability to evolve and innovate at a pace that matches or exceeds DirectX. So if like something happens and then DX somehow gets it and then Vulkan doesn't have it, I mean, it's just a matter of time, and it's not a matter of a lot of time. So it's gonna be fine. Alright, so imageless frame buffer, timeline semaphore, and then descriptor indexing and buffer device address. Imageless frame buffer is small, timeline semaphore is small, and then these guys are a bit more fundamental. So I kind of saved the meatiest topic for last. So let me talk about other things first. Imageless frame buffer is an example of a thing that I am very happy about. The reason why I'm very happy about this is it's kind of a pain. It kind of solves a specific pain point right now. It's required in 1.2, so, and it's not a hardware thing, it's just a software thing. So at some point, Vulkan renderers can be a touch simpler with the use of this. So what does this do? So people who are coming from the GL background may be familiar with the frame buffer concept. So, which is just a collection of render targets in GL, right? Collection of like attachments which you can render to. And Vulkan retains this concept, but Vulkan adds one new concept, which is render pass. And in Vulkan render pass, you can think of as the structure of your rendering path. Like, how many attachments do I have? what formats do they have, what sequence of steps should be performed to put them in the right like layout and formats and all of that. Do I use multisample anti-aliasing, etc. So render pass is a thing where if you render to cube map and you render to 6 faces of the cube map with 6 passes, you only need 1 render pass. So frame buffer, unfortunately, is a concept that DirectX doesn't have, that says, well, given this render pass, here's all of the resources, like images, etc. I mean, it's just images, to render, that I need to use to render to. And also here's the resolution of these. So like frame buffer says, so render pass says, I want to render things to a face of a cube map, and there's no multisample anti-aliasing involved, and like the thing is of format 32-bit color. Like RGB A8 or whatever. Frame buffer says, okay, also, the textures are all 100 by 100. Like that's my resolution of rendering. And also the color 0 texture is actually this specific one. So like 1, 2, 3, 4 handle. And like depth is this specific one. And so the problem is, and this doesn't come up as often in pure Vulkan implementations, like if you read a tutorial, it's like, yeah, I need to create a frame buffer. It's like slightly weird, but like whatever. But the biggest problem with frame buffer comes from trying to implement Vulkan support in engines that don't have the same concept exposed in their abstraction layer. And so I have 3 examples of why this is a problem, and they kind of go in the order of severity. 2 of them are from Roblox, 1 of them is not from Roblox, but it's a common industry problem. But what Imageless frame buffer does is it says, well, instead of specifying the resolution, the render path resolution and all of the attachments with their handles, we'll just specify like this part. And there might be something else that you have to specify for these attachments, but it's like inconsequential, roughly speaking. And so you still have to specify resolution, unfortunately. I will not talk about why, but you don't have to specify the actual handles. This means that you can create a frame buffer object without images, which is why it's called imageless frame buffer. And then you can specify the images to render to at pass begin time. So when you say CMD begin pass, and there's now like CMD begin pass 2 or something like this, you say, okay, it used to be that you just said, here's my render pass, and here's my frame buffer. And now you say, okay, here's my render pass, here's my frame buffer, and here's the list of images for my attachments that I will actually render to. And so this is much closer to how DX12 works, to how DX11 works, to how Metal works. Metal doesn't even have frame buffers in the first place, right? So this is like not quite all the way there. I would have preferred to just not have to have a frame buffer, but there are reasons why you have to have a frame buffer. So why does this help? So from like kind of in the order of severity, right? So remember, you still have to specify the resolution. So it's not like you can just create a frame buffer for each render pass or something like this and just call it done, because if you're rendering into, if you resize the window, roughly speaking, right, you have to recreate the frame buffer still. But here's 3 examples of why this is actually kind of interesting. And again, this is just reducing the software complexity of the rendering code, right? This is not, there is a new feature. This is not like there are performance benefits, like no. This is just reducing the complexity. But it's important to reduce the complexity of the rendering code. So the first problem is really straightforward. So if you have a swap chain has n images. And if you look at any tutorial code, any Vulkan code whatsoever, if you look at Niagara, if you look at like anything, you'll see, well, here's an image for each kind of back buffer that the swap chain provides, and here's the frame buffer, right? And it actually gets a bit painful because I think there's like you have to match formats or something, but I guess it doesn't change. Anyway, like if you look at our code, I haven't looked at this code in more than a year, but I'm assuming somewhere we create a frame buffer. Oh, I think we may have cheated. I think we are creating one frame buffer, but I think we are like copying it or something to the yeah. We are cheating. We are copying to swap chain instead of rendering to swap chain. Because honestly, I think I didn't want to deal with this like swap chain business, like swap chain frame buffer business, and just said, well, whatever, we're just gonna copy. Yeah, okay. So our code actually doesn't do that, but in most Vulkan examples, you would see them creating multiple frame buffers. And so with Imageless frame buffer, you don't have to create multiple frame buffers. You have to create one for the resolution of your swap chain, and then you can reuse it for all of the images. And so this is like a minor thing. This like removes a few lines of code from your renderer, right? Not that big of a deal. So that's like kind of minor. So the second thing comes up in Roblox, where we actually have a concept of frame buffer, but it doesn't map one-to-one to Vulkan, and it's kind of useful for us to keep it for some optimization reasons. But one specific problem that we have to deal with is that the way our renderer interface is structured is it says, well, when you render to something, when you render to a set of textures, right, to a frame buffer, you specify two things independently. One is you specify the frame buffer, which is the collection of render targets. And the other one, optionally, you specify a resolve target, which is necessary for this MSA business that I was talking about earlier, where we directly resolve to this. And in terms of us managing our high-level code, it's easier a bit to like split them up, so that the frame buffer doesn't contain the resolve target. It just, when you begin a pass, you can specify one. But this is actually a problem in Vulkan, because in Vulkan, these are part of the same thing, because the frame buffer doesn't just contain the render targets for the subpass that you're rendering to. It contains all images that are used by your render pass, including render targets, targets that you resolve to, targets that may be used by some other render pass, like who knows. And so we actually have like a page of code that is really scary, that tries to deal with this problem by creating the frame buffers and then remember, okay, this frame buffer in Vulkan actually is created because we have these high-level objects that need it to be there to render. But if one of these objects dies, we should destroy this frame buffer, because otherwise it's referring to an object that no longer exists. And so this tracking is like complicated. So if we had the Imageless frame buffer extension, which we now do, and it's now in 1.2, we can actually simplify this code to say, hey, when you create a frame buffer, like if you have MSA on this frame buffer, just create another one for resolving, but you don't have to specify the resolve target. But so there's a third problem that is worse, which is what happens if it's completely impractical for you to know the image handle at the point when you are setting up your rendering code for the frame buffer. And the way this comes up is in these like now popular render graph implementations, where specifically you want to do image pool behind the back of kind of the code that renders. So what this means is this: when you write the rendering code, you say, well, I want a pass that renders to an image of size. I have to keep shuffling this so that I have more space. So the way the render graph abstractions usually work is you say, well, I want an image with a format like R32F that has a size 128 by 128. I don't really care where it comes from, just like make one for me, right? And there is a chunk of code that is basically managing, that is basically managing these render targets. So let's call it render target pool. And this code can get pretty complex because the problem that you're trying to solve is this. You're rendering to a lot of different resources over the course of the frame, and each resource consumes memory. It's very tempting to be able to share this memory because maybe you render to something and then you don't need this memory again, so you can reuse this memory later. But that's a hard problem. And so there is usually a complicated code that says, well, let me try to find an image from the pool, and maybe when I allocate the image, I will try to alias it with some other image in memory. And so like, there's lots of complexity I won't go into. But what it comes down to is, you don't know the image that you're gonna render to up until you start rendering to the image, because this code usually lives in the kind of command scheduling code that says, here's the render graph, we've created some stuff for it before at some point in time, now let's like actually render to things. And it may be much harder for you to deal with the Vulkan restriction, because instead of saying, well, here's the render target pool, let's find an image that it matches the current requirements that's not used right now, etc., and use it to render, we know the format, we know the size, all of this doesn't change. Instead of doing that, you say, well, I found an image, now I need a frame buffer, but I don't have a frame buffer. Where do I get a frame buffer? So for render graphs, imageless frame buffers also reduce complexity. So that's great. The problem, of course, is that, again, there's no new GPU feature exposed here, there's no significant performance gains necessarily. Maybe for render graphs there's some amount of like performance gains, but it's mostly simplifying the abstractions that Vulkan provides you. The problem is that this is only in Vulkan 1.2, so if you have a renderer that has to support earlier versions of Vulkan, then you kind of have the old path that is still complex, right? And so that's not as interesting of a value proposition. But at least it's required to be supported by any Vulkan 1.2 implementation. So at some point in the future, when it's practical for you to say, I only support Vulkan 1.2, things can be slightly better. All right. It's really tiring to talk for like 2 hours straight. Let me catch my breath a bit. Can't even select this thing properly. Okay. Alright, we are done with this topic. So we finally have 2 left, and one of them is not that... Both of them are not that big, but one of them is like really important, so... Let's read chat. Is it prohibitive to create and recreate the frame buffer in case extension is not available? Yeah, you know what, it's hard to say. Like, on desktop implementations that I have seen, it's basically really cheap to create a frame buffer because the frame buffer doesn't have an actual kind of hardware component attached to it. So it's just create a bunch of memory structures. That is a good point. I forgot to brew tea before this. Let me set the kettle. So, yeah, so like on some desktop implementations, on all desktop implementations that I know of, it's very, very cheap, but on some mobile implementations, the cost is non-trivial. So, whether you want to do it or not, like whether you want to recreate or not, is questionable. We cache all of the frame buffers that we have to lazily create, but on desktop it might be okay, I'm not sure. Also, honestly, I think all desktop drivers will get support for 1.2 pretty quickly. NVIDIA and AMD already have one, so maybe it's a reasonable fallback, right? Because you don't need it as often. I'm gonna wait till my kettle boils and then I'm gonna drink some tea. Yeah, I always brew tea right before the stream, but I forgot, not forgot, but like I didn't time it right, and here we are. But again, we have two meaty topics left, so we will cover them in a bit. Let me check if I missed any questions, by the way, from earlier. Oh yeah, I didn't comment on this. Okay. What type of tea? So I was in France recently, and in France there's this cute brand. I'm gonna tell a brief story about this once my tea is done. All right, so a friend told. So this is like black tea, but right now I'm actually drinking a different thing, but this is the same brand. So a friend told me this. I didn't fact check this, but I'm assuming this is true. Uh, I can't emulate British accent. Hold on. So this is the brand, and it's a brand from Paris, and so this tea is actually, I'm not sure. Yeah, whatever. The thing can't focus right. This tea is the brand is not the brand, like the type of tea is called Saint Petersburg, which is actually the town that I was born in. But so the brand is Cosme or whatever. I'm not sure how you pronounce it in France, but the cute story about this is, and if anybody who's watching this is Russian or has Russian descent, they will appreciate this. So there was apparently a brand of tea called Kuzmich, and it was a brand in USSR at some point. It was made by a guy whose, I guess, last name or something was Kuzmich, and the guy relocated to Europe, presumably to France, and the brand kind of like was dying out, right? It's not wasn't very interesting. And then some company bought the rights to this brand and they rebranded this to say Cosmeti, to like make it more European sounding or something. I don't know. Again, I'm not sure how to pronounce this. And now it's a pretty prestige brand in the sense that you can buy this tea in Paris and probably in other French cities, and it's like you will see high-end shops that sell this tea. You will see this on like railway station. There's like a bunch of shops, and like one of them may be, I don't know, Louis Vuitton, and one of them may be this tea brand. The tea is fine. It's all right. It's not like particularly amazing, but it's pretty good, and I just found it very nifty that. So yeah, I bought two of them in Paris too. Just they're like expensive. This is like I forget. I think this thing costs like €6 or something, which is like $9. And for $9, I can buy a tea better than this here in San Francisco. That's like, I don't know, 4 times the size or 5 times the size. So it's pretty expensive. Anyway, so setting the Kuzmich tea brand aside, now that I have tea, I can actually drink it. Yeah, like it's not a bad tea, right? Like so it's distinctively good. It's just not the best that I have had. Like so, I think if it cost like a reasonable amount of money, it would be great, right? It's just that I think the cost versus balance doesn't really, the cost versus quality doesn't really work here, but it's not bad. It's just not like amazing, right? I have other teas that I actually prefer to this. It's just that this is reasonable, and like I brought it with me, so I have to drink it. It doesn't take too much time. So anyway, so mm, um, two questions I have not answered. So one question that was actually much earlier in the stream where somebody was talking about, well, wouldn't it be great if there was a Vulkan command that like created shader from shader source? And I actually disagree with this. And I think Vulkan made the exact right decision. So Vulkan is in many ways an API that is a compromise. There are many things in Vulkan that I wish were better, and even though I understand why they were done this way, like I think there were better ways to do them. But it had to ship. I think it was rushed because it was time constrained. Like Metal was there, DX12 was there, OpenGL was dying, is dying, it's almost dead. I don't know, and like there were many reasons, but there is at least one thing. I think there is way more than one thing actually that the Vulkan committee did very right, and one of them is the shader process. So if you guys don't mind, like let me just it's not really related to Vulkan 1.2 in any way, but I just it's a thing that I've wanted to see for a while, and I think Vulkan makes it much better. The entire ecosystem is still weird because of other vendors like Apple and some recent web GPU stuff, because from what I understand, because of Apple, may kind of make the whole problem worse again, but Vulkan made, I think, the exactly right choice. So okay, before Vulkan, there were APIs, basically DirectX and OpenGL, that took two different approaches to solving the how do you work with shaders problem. The OpenGL approach was, here's GLSL shader source. There is a spec, but it's a full-blown C-like language, but there is a spec for it. And then there's a driver that takes the source and then does magic things with that. And then the magic things produce GPU-specific assembly that kind of have the same semantics as the original code, but are implemented in the most efficient way possible. And there are a few big problems with this route. The problem number one is it's actually slow to compile GLSL, especially if we talk about low-end mobile devices. And I think part of this is their implementation is horrible, but part of this is that the device is slow. And like it's expensive to parse and compile C-like code. Let me give you one example. So in Roblox, at the point in time when we found this problem, we had, I think, 200 to 300 unique GLSL blobs. This is OpenGL ES, right? So GLSL ES. I can't remember the exact number, but like 200 to 300. And each blob is not crazily complex. It's like, I don't know, a few kilobytes of GLSL code. So like under like basically let's call it like 300 kilobytes of GLSL code. There was a device, a low-end device, where the first time you run the app, I think it cached. It didn't even cache stuff like we could cache. We just said, oh my god, this is so bad. We don't even like want to solve this sort of. But there was a device where the process of parsing not like compiling to GPU assembly with optimizations, like parsing took 20 seconds, roughly speaking, on this blob. So you start the app, and then like it takes it 20 seconds to parse shaders. Parse shaders, not compile shaders, like parse shaders. Okay. The second problem is you think you have a spec, which of course you do, uh, and there is even a validator for the spec, which maybe didn't exist at the beginning, I'm not sure. But not all driver vendors follow the spec exactly, and there was an NVIDIA driver was notorious for implementing the parser for this that kind of was following CG rules a lot. So you could write, I think this is valid GLSL in recent versions, maybe, I forget. But NVIDIA driver was notorious for being able to say like vec3 2, and then your shader doesn't compile on AMD driver rightfully because the spec says it should be 2.0 because 2 is an integer and there's no like implicit conversions. Back then they weren't. So like by forcing every driver implementer to write your own parser of GLSL text language, like you get many different implementations that de facto implement many different specifications. Then one other problem was, what if you have a high-level language that is not GLSL because you don't like GLSL? How do you translate to this? Well, you have to translate it to GLSL source, and in some cases, it's actually more complex to do this. Like if you think about the modern world of computing, there's a C language that is the de facto standard for like portable assembly, like a low-level language that maps really closely to the hardware. There's never a point where you're like, yeah, I want to do X, and C is like, yeah, no, you can't do X, or almost never a point. But if you look at C# or JavaScript or any languages like this, what they don't do is they don't convert their code to C and then compile that to native code. No, they have frameworks that work with not even assembly, like machine code basically directly through a series of layers of abstractions, but none of them are like C. And so there are reasons why this is the case. So if you want to compile by converting your code to GLSL and then compiling that, like, you should feel free to do that, but it's not always the optimal route. I'm not sure if I'm forgetting anything, but these were the big issues with the GLSL route. So then there was DX, which 9 through 11, 8 was a bit different, and 12 is sort of different now, but 12 began in the same way. The way that worked is there was DXBC. DXBC is a bytecode, so it's kind of like x64 machine code, right? But the instruction set is different. It works with vectors or floats and stuff like that. And there was an HLSL source language that compiled to DXBC. And this compilation process could happen on device, but the advice was to do this offline, like before you ship the code to customers. And then the driver consumes this bytecode, and then compiles this bytecode to the ISA, to the GPU specific instruction set. So this path was better in some ways and worse in others. Or I think it was universal. I think it was mostly just better, but there were still some problems that it shared, I suppose. So the good thing is this piece was owned by Microsoft. So there was no like 5 different versions of HLSL. Microsoft said, okay, this is the HLSL compiler. It's going to compile to DXBC. We can add new language features, which they did in some of these cases. Like there were derivatives added in like DX11 or something without changing the bytecode format. Without changing the bytecodes, you don't have to update the drivers, right? It's just the same bytecode. It's kind of like you can ship new versions of C++, but you don't have to have new processors, right, to work with them. So Microsoft owns this, and then the vendors consume DXBC. So this is good because it's faster to compile the high-level code to low-level code offline before you ship the code to users. and there's a single implementation of the compiler, so there's no like varied specifications. The problems were, though, if you wanted to use a different language, it was hard. Why? So DXBC was a format that was documented, but not. I don't know what's like the best words to use here, but basically you could not produce legally or officially, maybe is the best choice of words, but maybe also legally, I'm not sure, a DXBC blob from a different language. The only way to produce a DXBC blob was to use HLSL and use Microsoft HLSL compiler, which was closed source. If you had a bug in Microsoft's compiler, well, you had to wait for Microsoft to fix the bug. If you wanted to write a different compiler from a different language, such as GLSL, your only route was, again, just like in GLSL world, to convert to HLSL source and then use Microsoft's compiler. If you wanted to compile your shaders on Linux, which may seem weird, but maybe you have a Linux farm that's much faster and more cost efficient than a Windows farm, you couldn't really do this well unless you use Wine to run the Microsoft's compiler, which is, so and like there were no libraries to work with DXBC, right? So there's like a bytecode format, but it's internal. This, by the way, is the same approach, roughly speaking, that Apple takes right now with Metal. Except that instead of HLSL, they chose C++, which separate discussion point, but like I really wish they hadn't. And in the similar, they chose LLVM specific version of that for the bytecode, but they don't actually publicly talk about which version is it. How do I open up your like beautiful shader file and like extract this LLVM bitcode? How do I work with that? Like there's no interface, there's no nothing, there's no specification, there's nothing. So so Apple, I guess, arguably is even worse than Microsoft in that they don't even acknowledge the existence of this bytecode format. Like Microsoft documented DXBC, like you can go on MSDN, you can find documentation for large parts of DXBC. There are some parts that are not documented, but they are documented, like people reverse engineered them, but like large parts are documented. And so like it's not actually a big deal to parse this bytecode in your program. It's just hard to make it yourself because of some complexities. So here's what Vulkan did. Vulkan said, well, we're gonna make bytecode. There is one more problem with DXBC that some vendors hit, which was DXBC was based on vector instructions, and the HLSL compiler actually spent a fair amount of time kind of vectorizing computations to use the vector instructions, which was a good idea back in the day, but it's not as good of an idea now. But it's not really endemic to DXBC. It's endemic to the specific optimizations the compiler used to do. Here's what Vulkan did. Vulkan took this entire thing and said, okay, let us solve this problem in the best way possible. And I genuinely think that they got basically the best result that they could get. There's one thing that they could have done slightly better, but that would have compromised some other things, so it's like, fine. Here's what they did. They said, okay, we need bytecode, because if you're just gonna like specify GLSL like 4.5 or whatever, or 5.0, it's gonna be the same thing again, where different drivers have different implementations, the compilation process is slow, etc., etc., etc. So we need bytecode, and the bytecode is called SPRV. The bytecode will be the way how you talk to the API in terms of shader, like bytecode, and we will document it, we will provide libraries, we will provide, like, it's gonna be an actual official supported thing. Because with Microsoft, DXBC is part of the internal implementation. The actual interface is HLSL. It's just that they provide you an offline compiler from HLSL to DXBC, like Apple does. But DXBC is not the interface is really HLSL, so to speak. So there's a specification for SPRV, there is a set of tools for SPRV. So there's a validator, which looks at your SPRV code and says, hey, is it valid SPRV? Microsoft doesn't have this for DXBC. Well, I mean, I'm sure they have it internally, but, I've never seen it. So there's an optimizer which takes SPIR-V and says, hey, let me apply a bunch of optimizations that I think will help no matter what GPU this executes on. And there's many optimizations that it does, and you can say, well, I want this one, I don't want this one. And you can't work with SPIR-V as your only kind of source of truth, right? Like you can't write SPIR-V code by hand. Oh, also there's a disassembler, which converts it to human readable implementation from the binary representation, and assembler which converts it back. Then there's GLSlang that can consume either GLSL or HLSL as the source language and produce the SPIR-V blob. And then you can choose to run GLSlang offline like we do, or you can embed this into your shipping game and use it live. Also, there is now wrong color. There is now DXC, which is actually the effort is started by Microsoft, but then Google kind of became involved and added support for this, which can take HLSL and also convert it to SPIR-V. And DXC was born for a different reason. I'm not going to talk about this, but there's like 2 different compilers. Also, there's other tools that can emit SPIR-V. I think somebody had a experimental, I've seen like an experimental Rust to SPIR-V compiler, and like you can write your own toolchain that converts from whatever language you want to SPIR-V. And this entire stack is open source. So no longer it is the case that HLSL is your only language, that's the interface to the API. You can make it your own language, or you can use a language that the community has standardized, like GLSL or HLSL, right? But the compiler is open source, and it's not the actual interface. Like the actual interface is SPIR-V. So if you find a bug in the compiler, you just fix a bug. You can fix a bug by yourself. You can wait for somebody else to fix a bug. You can ship a bug fix. You can add a new feature to GLSL and not like share it with the world because you want your own private like fork of GLSlang, right? And all of this works because the driver sees SPIR-V. So it's the model that's roughly as robust as the DX911 model was from the driver perspective, where you see this bytecode that is more tightly specified, that doesn't have like weird source differences. And there is a spec and there's a validator and all of that, but as much as possible is open source, and you can write your own tools around the same format. So this is what Vulkan did, and then there's other really nice bits out of this that we got. We got SPIR-V cross, which can take the SPIR-V blob and convert it kind of back into the source representation. So it's kind of like a disassembler, like a decompiler, and it's really handy. Like we use it right now to compile shaders to metal and whatnot. And so if other APIs adopt SPIR-V, then things will be great. Of course, like Apple will never do this because Apple is Apple. Microsoft has made their own thing that's kind of like SPIR-V that is not SPIR-V, which is called DXIL. So they will not do this either, I suspect. But so this is the choice that Vulkan made, and I think it's exactly the right choice. And I think honestly, the resulting kind of ecosystem of compilation tools is far superior to anything that has existed before this on the shader side. And yeah, that's why I don't think there should be a function that takes a shader GLSL source and then just like creates a shader object from this, because this defeats the purpose. Like this is tempting, it's simple, but it creates so many problems down the line. There was actually an extension that did the exact thing. I think it's like VK and V GLSL shader, but they deprecated it now because it's the wrong thing to do. It's tempting, but it's the wrong thing to do. All right. Brief shader digression aside, and by aside I literally mean I'm gonna move it. Let's talk about the 2 remaining things I wanted to talk about with respect to Vulkan 1.2. So, if you want to generate shaders at runtime like a shader editor when you would ship GLSlang, absolutely, you can do this. So you could ship any compiler. GLSlang is a compiler that is pretty small in terms of the binary blob that it produces. If you don't embed optimizer and whatnot, it's pretty small. If you embed the optimizer, it's a bit larger. So like this is the compiler actually executable is like 7 megabytes, which, you know, it's you probably can cut parts from it away. I think the biggest thing here is actually the optimizer. Yeah, the optimizer is like 4.5 megs, and I think in this in the validator it's statically linked. But this executable actually has both GLSL and the GLSL compiler and extra things. So like if you just wanted to compile GLSL to SPIR-V, it's a smaller binary. But yes, absolutely, you can compile it as a library. There is also the library called shader-c, which I think Google made, which is a slightly nicer library interface. But yeah, like if you want to make a shader editor, nothing stops you because it's open source code. You can compile this open source code into a different configuration. You can change it however, like nothing stops you. The optimizer. So if you use HLSL as a source language, the optimizer is actually ran for you. And the reason why that is because there is this complex process called legalization where the when HLSL code specifically is converted to Vulkan, the compiler usually converts it to a SPIR-V that might not be valid for complex reasons, or there's like parts of this that are not valid or something, and then it optimizes it, and then the optimization process makes it valid. So it's a bit complex. If you start with the GLSL shaders, the optimizer isn't ran for you, so you can run it yourself. Whether the optimizer has significant performance gains depends on the drivers, because a lot of drivers have their own optimization pipelines. It's actually sometimes is the case that some of the offline optimization passes fight the driver optimization, but this is, I think, an ongoing process of like making this whole thing better. You can choose to not run the optimizer. You can also choose to run the optimizer for the size reasons. A lot of games have lots of shader combinations, and you end up shipping like hundreds of megabytes of shader code. And if you run the optimizer, it makes the shaders much slimmer, so that's good. In all of these other pipelines, which I already moved aside. So in DX9, 11, the optimizer is run offline, like HLSL compiler runs it, right? In Metal, again, there is some amount of optimization, actually I think a fair amount, that runs when the Metal compiler compiles Metal source code to the Metal IR, it's called, intermediate representation. So mostly people use, like most of the stacks use offline optimizers. Now, like if you talk to some graphics vendors, they will be like upset about the offline optimization, because they'll be like, yeah, like it makes this code harder to understand for my driver, and so my driver loses performance on this. But I think it's a continuous kind of tuning process. Do you go from HLSL to MSL or from GLSL to MSL? So our shader pipeline looks, now, it used to look like this. It used to look like we basically did the source-to-source translation. There is a library that we used to use, which is called the HLSL parser, which it's a nice library. We contributed a lot of changes to this. This is the ground truth repository for this. It's used by Tekla, which is the company that made the Witness, which is which has been released like a year or two ago. It's basically like, if you know Jonathan Blow, this is his company. Anyway, so we used to use this, but this only supports DX9 HLSL syntax. We couldn't run compute shaders and stuff like that. So we used to the pipeline that I think is now basically the de facto standard for across many companies, and I think many companies that use different pipelines are adopting this. The pipeline looks like this. We use we start with HLSL because this is what our shaders are written in. Then we compile HLSL to SPIR-V. We use GLSlang for this, but many other companies use DXC for this, because DXC is if you start with HLSL, DXC is a slightly more faithful compiler because it honors the HLSL specification a bit closer because it was written by Microsoft, right? So, but honestly, we use GLSlang. It's fine. It works great for us. Some people don't like to compile HLSL with GLSlang. I think some folks hit issues with really crazily complex shaders. Like if you have shaders that use every single feature of HLSL, including the ones that nobody knows exist, then maybe you should use DXC. But like whatever, it doesn't really matter. Anyway, so then we optimize SpearV using SpearV opt. The repository on GitHub is called SpearV tools, but it's basic. There's an optimizer and a validator in that repository. So we do this to keep the size small of the blob. In some cases, we see performance improvements for this. In some cases, we see fewer bugs because we run the optimizer, because the optimizer makes the code simpler, so the drivers are less likely to like miscompile it. In some cases, we see more bugs, so it's complicated. And also, we have a few custom optimization passes that do some transformations on the SpearV level that are like relevant to us. And then for Vulkan, we just ship that. So that ships to our users, right? For other APIs, we use fantastic SpearV cross library that can take a SpearV blob and produce GLSL for this, which seems pointless, but if you ship OpenGL code, you still need GLSL because OpenGL up until desktop OpenGL 4.6 or something doesn't understand SpearV, and also MSL, which is Metal C++ code, right, which we then compile offline to the Metal, I think it's called Air. But this is a proprietary format, and this compilation is also proprietary. Like it uses proprietary apples built of Clang, so we don't know what it does, but it results in binary files. It's also slow. Like this is by far the slowest part of our Metal compilation pipeline because MSL is C++. Turns out it's slow to compile C++, especially if you use templates, which Metal standard library does. Anyway, so that's our pipeline. And we've contributed a bunch of code to SpearV Cross as well to make the GLSL portion nicer. So yeah, that's what we do. Zip your SpearV for shipping. Yeah, like if distribution size is important for you, you should use obviously general purpose compression. One other thing that you should probably use if distribution size is important to you is to use the thing called small v. Small v is, we don't do this right now because our entire shader blob is like under a megabyte, so it's like whatever, who cares. We very consciously keep our set of shaders small. But if you want it to be smaller, you can use small v. So what small v does is it takes the SpearV blob and it processes this to a different format. So it provides a codec and a coder and a decoder, right? And so A, your SpearV blob gets smaller, but B, the output of the compressor is more compressible. So the expected configuration, if you want the minimum size, is that you take SpearV, then you use small v to produce like whatever binary format it produces, and then you still use gzip or something, or like z standard, better, like, or lz4 or something like this. Let's say z standard to compress it. And that results in the file of basically the minimum size that you could get with modern tools. And it's a fast codec, so it's not really slowing things down to like have to decode this data when you load. Anyway, all right. All right, so moving on. Let's actually finish talking about the things that we have left to talk about, and then if there's further questions, I'll answer the further questions. Kind of want to end this in like half an hour, so yeah, I don't, we will not talk about this PRV stuff. It's mostly trivial. And I covered some of this before. It's not super interesting. There's one interesting feature which is marked with the check mark. Maybe we'll talk about this, maybe we won't. Okay, so let's talk about there's three extensions, but there's really two topics. One is timeline semaphores and one is the bindless stuff. So timeline semaphores. So the idea is like this. In Vulkan, if you want to synchronize CPU with the GPU, you use fences. And there's also events which you use to synchronize GPU with GPU. And there's also semaphores, other, whatever. Let's just call the synchronization primitive that we want to talk about fence. This is what we use to synchronize between CPU and GPU. Fence is a thing that can be in two states. It can be 0 and it can be 1. It can be signaled or non-signaled. And so what you can say is you can say, I want to wait. I want to wait for fence, right? And what this means is, let's say this is a command that you execute on the CPU, right? Which is how fences work. So what this means is the CPU will stall, and when the GPU raises the fence, which is why it's called the fence, right? I guess. And this means signals the fence, so this means puts the fence from 0 to 1. Then the CPU can stop waiting. And so this is handy if you want to do things like, hey, I want to wait up until the GPU is finished rendering the frame, which is one of the core things you want to do in Vulkan, because this tells you whether it's safe to release some resources, right? So that's nice. However, there is a more general version of this. And if you look at DX12, the more general version looks like this. Instead of saying wait for fence to be signaled, you say wait for fence to become greater or equal than v, where v is a 64-bit integer. And instead of saying I want to signal the fence, you're saying I want to, and I forget what the DX12 terminology is, but basically you're saying I want to write the fence value of v, which is again a 64-bit integer. And so if the fence value is 0 or 1, then it's kind of the same thing, right? It's like if the fence is 0, you say I want to wait for fence to become greater or equal than 1, and then I want to write 1, and then once you write 1, the wait is lifted. But the value-based primitive is much more general. For example, so I'll give a few examples of why this might be relevant. This feature is useful for two reasons. So it's like required to be supported in Vulkan 1.2, which is great. It's just a driver update. GPUs can do this. Once you get a Vulkan 1.2 driver, if you are fine with requiring Vulkan 1.2, you can simplify your synchronization code by using these. And if you're writing DXVK, then it's going to be hard for you to implement fences from DX12 without support for this extension, because Vulkan doesn't know how to do this, so you have to emulate a lot of stuff, and it's really hard. So why is this easier to use? So here's one example. Here's the basic example that every single Vulkan tutorial runs into. Maybe not every single one. Some don't. I don't think actually we use fences, because when we started the project I said I want to focus on GPU stuff. I really don't care about the CPU GPU synchronization, so I'm just gonna wait for the GPU to become idle after every frame, and I think I still do that. We have a semaphore because you need them for presentation, but that's a different story. That's like a GPU to GPU thing. Yeah, we don't have a single fence, but we aren't doing things right. Maybe at some point I'll do a stream where I start so I was actually thinking maybe it would be actually an interesting kind of at some point, maybe next week or something, I could do a stream where we take Niagara and convert it to Vulkan 1.2, because actually timeline semaphores, we don't need them right now, but if we were to do things right, we would need them, and then a few other things from this we would need. Anyway, so you have a renderer and your renderer submits frames, right? And so for example, your renderer has to submit the command buffer, right? So I think the thing is called vkq submit, and inside it there's a command buffer object. Oops, command buffer. After you submit the command buffer, it's kind of on you to release the memory that this command buffer holds. But you can only do this when the command buffer has executed on the GPU. So to do that, you have to be able to ask, is the command buffer ready? And so this is what fences are useful for, right? But the fences are only 0 or 1. So there's a few implementations that you could kind of use for this, right? One is, okay, whenever we submit a new command buffer, we're just going to create a new fence. It's in value 0. And then we're going to use that fence to wait for the command buffer, and then we're just going to destroy this fence. The problem is fences are expensive to create and destroy. There's a kernel object back in them, and there's usually a non-trivial amount of work involved in like creation and destruction. So you don't really want to create and destroy fences all the time. You want to reuse them. Well, and this is what you usually do. So what you usually do is, for example, you say, okay, I want to have at most 3 frames in flight. We do 2 to reduce latency, but canonically you would do 3 because this is closer to what DX11 like APIs do. 1 frame is recorded by CPU. Another frame is being executed on GPU. And then 3rd frame is also executed by GPU. So you can be at most like kind of sort of 3 frames behind. And you may want to just keep 2 because that's less latency, but this means that if there's suddenly a difference in GPU workload, you might see a frame drop, and it's a bit harder to balance this. And so what you do then is you say, well, I need 3 oh, wait, where does it... So what you say is I need 3 fences, 1 for each frame, right? And then at the end of the frame, I'm gonna submit my command buffer, and I'm gonna say signal this fence when it's done. And then when you start recording the new frame, or when you end recording the frame, you say, when you end recording the frame, you say, well, I want to wait for the frame that is still in progress on the GPU, because, how do I put this? So you want 1 frame to be recorded and 2 frames to be executed, but once you submit the frame that you have finished recording, you will have 3 frames that are executed on GPU. So before you submit, or after you submit, or whatever, usually before, you say, well, let me wait for effectively this guy, and then do the resource cleanup, like release command buffers. Maybe there are some resources that you can destroy, etc., etc., etc. And then you can execute your, like, submit your Q frame, and now you have, again, 2 frames executing on the GPU. So you need 3 fences, right? So you need a fence for each frame. Because it's fine to track submissions of kind of all command buffers in the entire frame. But what if you want to track submissions of each command buffer individually? Well, then you need more than 3 fences, right? You need like however many fences you have, however many command buffers you have, or whatever, right? So with the value-based fences, which is called timeline semaphores, I think, in Vulkan now, what you can do is you can actually say, no, there's like 1 fence, and on the CPU, I know in this frame example, right, I know the frame index, which is a number, a 64-bit number, so it basically never overflows. Every frame you increment it by 1. How do I wait for the GPU to have finished executing? So let's say I'm right now recording frame number 75. How do I wait for the GPU to finish processing up to two previous frames? Well, it's easy. The frame before me is 74, the frame before me is 73. So I say wait for fence to become greater than or equal than 73. That's it. One phase, one value that sequentially increases. And then at the end of this GPU frame, I say, well, I have recorded frame number 75. Cool, can you update the fence value to be 75? That's it. That's all there is to it. So if you just have three fences, I mean, who cares, right? It's not actually that much simpler. But there is one case where if you have a primitive like this, it's much easier for you to deal with synchronization. And I don't necessarily recommend doing this because there are easier how do I put this? There's like ways for you to structure your synchronization code so that you don't need this necessarily, but sometimes you really do. And when you really do, if you don't have this primitive, it's really, really hard. Like in general, DX12 doesn't even have binary fences, it just has value-based fences. This extension, it basically mostly replaces, like, you don't truly need binary fences if you have a value-based fence, because as I was saying earlier, it's just a superset, right? Like, you can do everything you can do previously with fences, with like timeline semaphores, but you can do so much more. So here's the so much more example. And I need to move things around. So imagine that what you want to do is you want to send data to the GPU in a buffer. For example, let's say you have constants, and you decided that what you want to do is you want to have one large buffer, which is like, let's say 16 megabytes, right? Whatever the number is, doesn't matter. And CPU writes constants to this, and then GPU reads constants from this. And so CPU writes like a block, right? And then tells the GPU, okay, like this is the offset in this buffer that you should read from. Cool. And then the buffer is a ring buffer, because like, okay, so it's finite sized, right? And so if you want to reuse the same buffer multiple times within a frame, which for some rendering structures is actually useful, then it has to be a ring buffer. If it's not a ring buffer, then basically you probably need one buffer like this per frame. And so instead of one 16 megabyte buffer, you have three 16 megabyte buffers. But then what if you run out of space? Or what if, like, I mean, that's a lot, right? So, but what if you run out of space in each frame? So then your memory consumption is like higher because you have to accommodate for the peak use in each individual frame. But if some frames have 10 megabytes and some frames have 2, then it's like really unbalanced. And this can come up in resource upload buffers and like all sorts of cases. Okay, so it's a ring buffer. So this means that generally speaking, the CPU writes ahead of the GPU. So CPU writes a bunch of stuff. Now this thing can be read by GPU. And the CPU can continue writing here because the GPU doesn't read this, right? So it doesn't matter, up until the wraparound. So the question is, when the ring buffer wraps around, how does the CPU know that it's safe to overwrite the existing data or not? If the GPU is still reading this data, it's not safe. The classical synchronization method for this involves using what's called a get pointer and what's called a put pointer. Put pointer is the current write location from the CPU, and put pointer goes to the right. And get location is the read location on the GPU, and this also goes to the right. And so on the GPU, you may do something like this, where you submit commands for reading this somehow. This may be a draw call, this may be a copy, whatever. And then you say, okay, I'm done with this segment. I don't need this anymore. Let me update the get pointer, which with the timeline semaphores, I don't actually know what the command looks like. Let me look it up. So that the theory is slightly more connected to practice. Um, I'm suddenly wondering whether this feature can actually be used exactly like I'm talking about, because great. So this is how I discover that this primitive is actually weaker than what DX12 offers, because DX12 allows to do this on the... Oh no, it's on the command queue as well. Okay, no, yeah, that's fine. That's the same thing. Right, I guess. Okay, never mind. Okay, so like in an ideal world, this is how you would do this on, let's say, on like low-level APIs that Vulkan or DX12 aren't. You just say cmd write fence, and then it updates the get pointer with the value like after the point that you have read. And so on the CPU, we are saying, well, if the get pointer is like 17, then it is safe for us to write things to like values before the 17, right? But it's not safe for us to write things after the 17. And so what you want to say on the CPU before you write is you want to say, I want to wait for the fence value to become greater or equal than 17, and then I can write to memory kind of before that value, right? And then it's a ring buffer, but you can have this fence be sequential 64-bit integer that by itself doesn't wrap around. So it's like each location in the buffer corresponds to to multiple values in the 64-bit space. And then to translate it into DX12 and Vulkan terms, apparently, you can't actually write the fence after each read command, but you can write the fence after the entire command buffer because it's a queue operation. So you can submit the command buffer, and then you can say, well, I want to update the fence value to the kind of maximum of everything that this command buffer has read. All right. And so this type of synchronization... So we actually, in our renderer, we used to do this in a few APIs, but not Vulkan. So because on Vulkan, like, there was no way to do this, and now there is. So maybe we will use this, maybe not. I don't know. We'll see. But like, point is, so this is, you have to have this for DX12, but also some operations get easier if you have a primitive like this. It's unfortunate that it's not like cmd write fence. I know why this is, I think, but it's unfortunate that you can't just like update this in any instruction in your command buffer and then just have the value kind of be updated. Because if you had this capability, you could be very granular about your synchronization. I think this runs into the deadlock problem, which is that I think one of the goals of all of these APIs is to be able to detect incorrect synchronization before you submit work to the GPU. So it's not like, so you have to have a forward progress guarantee. The bad case is like this: there is an API, you can use this API, but if you use this API wrong, your entire system like deadlocks because the GPU can't proceed past the signal, and you have to reboot it completely, right? So that's like a bad graphics API in the modern world. It's fine on consoles probably, but it's bad graphics API on desktop or mobile devices, right? So I think this is why there are some restrictions around this, so that if you are trying to update the fence to the wrong value, like wait on the wrong value or something, it can be detected more ahead of time. But I don't actually know how much guarantee the current specification provides, so who knows. Anyway, so these were timeline semaphores. You know what? It's actually will be easier for me to move things out of the way like that, because there is so much here. Oh, I understand how the move thing works now. Okay, yeah. Okay. Okay. All right. Whew. All right. One meaty topic left. Yeah. So the question is, does this mean your program will break after 4 billion years of running time? Probably. I think that's right. Oh man, yeah, we are approaching like 3 hours, which is kind of nice. If you have shaders running in parallel which depend on each other with time on semaphores, you don't have to worry about transmitting the command buffers in sequence and can submit them out of order. Yes, that is probably true. So I think largely speaking, the point is if you start thinking about synchronization in terms of this, like, sequentially, not necessarily sequentially, but like increasing number that is 64 bits, so it might as well be infinite. Um, as opposed to the binary fences or like binary semaphores or whatnot that we had so far, then things become easier. Um, I think it's also the case. I'm fuzzy on. I think in Vulkan there were like some restrictions around the use of, like, the reason why there is not in Vulkan there's fences, events, and semaphores, and so in Vulkan 1.2 there's now this timeline semaphore, but not a timeline fence. And so I think the reason is because it kind of supersedes both fences and semaphores, but just not events. Anyway, all right. So we have two things to talk, technically three, but who knows? The subgroup broadcast dynamic ID thing is kind of arcane. Like, I will have to explain subgroups before I explain this. So maybe we'll just punt on this. But the big thing I want to talk about is the bindless stuff. So there's two extensions that we haven't discussed yet. One is descriptor indexing and one is buffer device address. And they're sort of similar. You don't truly need the buffer device address in many cases, so it's kind of optional, but I kind of want to talk about them in concert because just like the structure layout improvements that we talked about in the beginning of the stream, they form a theme. And the theme is how can we have our GPU code be more free to implement various rendering techniques without the CPU code having to work with it so much. And so specifically, let's talk about something that we have actually done on stream, but just not with the use of these two extensions, which is a fully GPU-driven renderer. And so what we did on stream, like again, like it was a year and a half ago, there's a playlist with this stuff, but roughly speaking, what it boils down to is instead of saying that on the CPU we will identify visible objects, and then for each visible objects we will do the setup, right? Which is what it usually works as. So we do like frustum culling and occlusion culling, and then for each draw call we do like texture binding and constant update, and then like shader bind, and then draw call, right? And so these things are agnostic of Vulkan or any other API really, and these things are very specific to the Vulkan or GL or whatever. And then you have the GPU, which basically just says process the draws. Instead, what if CPU wasn't really involved at all? What if CPU said, paraphrasing, because it's not quite like this, but what if CPU said just render the scene? That's it, right? And then the GPU did all of the rest. And so why do you want to do this? Well, it turns out GPUs are generally speaking faster than CPUs at doing certain things. And this offloads a lot of work from the CPU. And some of this work is actually really hard to do. So like, let's talk about occlusion culling, right? How to do the occlusion culling on the CPU? It's actually really hard to do it well. You can use the depth buffer, but then you have to render the depth buffer. You can render it on the CPU, that takes time, and it takes potentially a lot of time. And then you can render it on GPU, but then you have to use the buffer from a few frames back, and then your occlusion culling is imprecise. Maybe you don't use the depth buffer, maybe you do geometrical occlusion culling, but that's a really hard problem, and then some things don't work quite as well. It's really hard to do occluder fusion, which is when each occluder individually doesn't occlude an object, but when you look at both of them, they kind of do in concert. This is called occluder fusion. It's hard to do this if you do geometric occlusion methods. So it's a hard problem, like how do you do this? On GPU, it's easier because you have a rasterizer, you have faster access to some things that you may have rendered before, stuff like that. So if you're doing frustum calling, it may take a lot of time, so you can do that in parallel using multiple threads, or you can do this on GPU where there's a ton of threads available to you. Of course, the problem is on the GPU, you have like one GPU, right? I mean, maybe you have two, but most people have one. And of course, if it takes a lot of time to do this work on the GPU, then you're actually making the system slower. But usually a lot of the stuff is reasonably fast on the GPU or really fast. And also the other thing is, so if you look at this stuff, some of the problems in this space around this code being slow are kind of like stupid software problems, meaning here's my 3 layers of abstraction, and here's a driver, and who knows what the driver does, and here's some other bit of code, and who knows what that does, and every little thing takes a bit of time, and you never know how fast it's gonna work, and it's just like, it's hard to make this code run at the top performance of what the CPU is capable of. People do this in console space, it's hard to do this in non-console space. This is why in OpenGL, there's this technique called achieving zero driver overhead, which is a terrible, terrible, terrible name, but this is what it's called, and this is what people refer to kind of in various contexts. And what this means as well, instead of asking the driver to render stuff, can we like ask the driver to render the scene, and then in our shaders we will somehow render the scene without the driver being aware of each individual draw call in its setup. So so then on the GPU, right, you do like all of this stuff. There's one other context in which what I'm going to talk about becomes really important, which is actually ray tracing, which is, there's somebody asked the question about this, right? And the thing with ray tracing is the thing on the left doesn't even work. Because the thing on the left says, let me submit each object with its own setup one by one. But that's not how ray tracing works. The way ray tracing works is you say, I want to cast a ray through the scene. The ray hits some object, I don't know in advance which object it is. This object has a material, the material has some textures. I need to sample these textures, I need to compute some BRDF functions, I need to do a whole lot of work. What if the surface is reflective? Okay, I guess I'm spawning another ray. It hits some other object, who knows what that object is, right? So the left side doesn't even work for ray tracing. The right side is kind of the only way to do ray tracing, with GPU acceleration, of course, right? So the question though is, and so this is what we did in the streams from not last year, I keep referring to this as last year, but I think this was end of 2018. So the reason why we were able to do this is because we took all of the data that we have, which is not that much, but we basically support geometry, so we can render a bunch of different meshes with different geometry. Most of the screenshots that I had from that prototype project are like one mesh instanced a billion times, but we actually were showing an ability to render multiple different meshes. So what that code could do is it could render a scene with an arbitrary number of arbitrary meshes with no materials whatsoever. The way it did this is it said, well, all of the information has to live on the GPU. So we will have a buffer with mesh descriptions, and then we will have a geometry buffer. And actually there's like a few of them. There's like vertex, index, meshlet, stuff like that. And it's just a giant buffer that holds like everything, and then mesh buffer has offsets that go into this giant buffer, right? And this is kind of how we work with that. And then there is a set of compute shaders, mesh shaders, vertex shaders, whatnot. The technique doesn't require mesh shaders. Mesh shaders make some things easier, but you can do this without them. We did this without them as well. The key thing is all of the information has to be accessible to the GPU, and you have to be able to work with all of this information reasonably easily without large performance costs, stuff like that. And so this is where the two extensions that we haven't talked about yet come into play. And so colloquially, this is called as bindless. This is referred to as bindless rendering, which is a much better name than AZDO. It's still not a great name because it doesn't really accurately describe what's going on, but there's a reason why it's called like this. So let's talk about one problem that we actually had in the demo that one of these extensions can help correct, and then I'm just going to talk about another one. So when you're just dealing with buffers that contain data, it seems like, yeah, you can just create a giant buffer and then put everything into that buffer. But then the question is, how big should this buffer be? And I think for us, the answer was like, I don't know, some amount of megabytes. Let's find. Yeah. So I think for us, the answer was, well, I guess we're going to create a few buffers, and each one is like 128 megs, and hope that's going to be big enough. And if it is, it's fine, right? I didn't get to this, but ideally, you would just create one buffer, not like 3 different ones. But then you have to allocate data inside these buffers, which is not very hard, but like, so, but this is one approach, right? One approach is just to say, here's one super big buffer, like we say there's going to be 256 megabytes of geometry in the scene. And then maybe if there's more, you can like reallocate this buffer. And then if you want to do streaming, like geometry streaming, then I guess parts of this buffer will have to be evicted, so like you don't need this space anymore. And then you can put other things in the space that they were occupying. So you can write an allocator. So this is all doable in theory and in practice, and you could do that with buffers, not with textures, but with buffers you could do that. However, notice that on CPU we usually don't do things like that. On CPU it's like, okay, hey, I kind of want a buffer object, well, just allocate one, right? And then there's some heap magic that kind of works with that, but it's not restricted to here's this one giant linearly addressed buffer that is, by the way, resident in memory, in physical memory. You can allocate things in different places, and you get pointers to things, and then you can refer to an object by a pointer instead of by an offset in one giant buffer. And so this is what the buffer device address does. Now, there are some caveats. So it's not the case that you have to, or maybe even should, do this in all cases. But what you could do is that instead of the mesh buffer, and I can show the structs because we did all of this, right? Like if you look at, there's a mesh struct somewhere, and it has like vertex offset and vertex count. And so what vertex offset is, it's an offset into this giant geometry buffer where the vertices of this mesh are, right? And instead of doing this, you could say, well, here's a mesh, and my mesh has a buffer pointer for the vertex data. Or maybe for both vertex and index data, or maybe for everything. Maybe, like, you probably should, like, pointers are larger than indices, so maybe you only have one pointer, right? And then in your shader, you literally dereference this pointer. You literally say, well, like, it's a pointer, I can read data from it. And then on the CPU side, you don't know what the value of this pointer is, but on the CPU side, what this buffer device address extension gives you is an ability to, on the CPU, ask, hey, here's this buffer. Can you give me a 64-bit integer that I can pass to the shader, and then the shader can use this as a pointer, and then the driver will implement all of the rest. Let's look at the function in question that does this. And there's some like plumbing around this. You have to create a buffer in a special way so that you can get the address from this buffer. And then when you pass this to the shader, there's some new PRV structures so that shader can actually read this and work with this. But fundamentally, here's the function. The function returns your VK device address, which is like a pointer. But it's not a pointer that you can dereference on the CPU, but it's a value that when you pass it to it's a 64-bit value, and when you pass it to the shader can dereference it. And you just ask it for a buffer. That's it. And you get a pointer to the beginning of the buffer, and then you can dereference any value inside this buffer. And if you have out of range access to this buffer, you're on your own, just like it is on the CPU. It's a bug, maybe the GPU will crash, who knows what will happen. So this is groundbreaking, right? This is saying, wow, instead of binding a buffer for the shader to use, I can get a persistent pointer to the GPU memory that refers to the data of this buffer, and it's just an integer, right? And then I can pass it to the shader. However, I can pass it in a uniform buffer, I can pass it in a shader storage buffer, I can pass it in a push constant. I can have another pointer in that buffer that refers to another buffer. So you can literally build a linked list of buffers. Now, like, to be clear, whenever you create a Vulkan buffer, especially the buffer that has a physical address, there's got to be all sorts of overhead in terms of memory. Like, you should not create a 10-byte object, just like you shouldn't do this on the CPU, but on the GPU it's even worse. Like, you shouldn't create a 10-byte object and just say, yeah, well, I guess this is the 10 bytes that you should reference. Like, your objects, I don't know what the actual alignment restrictions here are, but I feel like if it's less than it's probably the case that if it's like more than 4 kilobytes or something, it's probably fine. If it's less than 100 bytes, it's probably not fine. If it's in between, who knows, right? But this opens up possibilities, right? Maybe you still want to use integers to offset into this buffer, but maybe, so for example, one kind of middle ground between this is this. So let's say instead of just having a buffer, a unique buffer object for each mesh, instead what we say is, well, when you load a model, the model gets one buffer. The model might have many meshes inside it and who knows what else. So you'll get one buffer, and then you'll pack everything else inside this buffer, everything that the model needs. And so instead of this, you get something like buffer pointer, like base address, which is your model data. And then you still have vertex offset. That refers to the byte offset from the base address to the vertex data. But the difference is, instead of saying all of the meshes have to be in one giant buffer, now the CPU management code can decide, well, here's the giant level, here's the giant buffer for it that everything else lives in, here's the buffer, here's the pointer to the buffer, let's create a mesh structure that points there. Or it can say, well, I guess this is like one small model and there's some overhead to create a buffer for it, but like, who cares? Here's the new buffer, here's the pointer to this buffer. And the rendering system doesn't have to care where the data came from, because here's the base address, just do whatever you want. So this is kind of a big deal in the sense that it substantially expands the amount of things you can implement with buffers. It gives you pointers on GPU that point into buffer memory. And the natural question is, buffers are cool and cute, what do I do with textures? And this is where the second extension comes in. Let me move this away, look at chat, and then I will talk about the second extension. Oh dear, this is like a 3-hour stream. Yes, thanks Yuri. So Yuri points out that there's an MD specific extension that is a bit closer to what I was talking to about the like low level fences, where you can write an object from the command buffer from inside the command buffer, not from like the external boundaries of the command buffers. So not from the queue, but from the inside of the buffer. But it's MD only. I don't know if you can wait on it or if it's just like if you can just read the value from the CPU, so you have to poll. So, but yeah, it's an MD extension. Out of all these extensions, which do you think will be the most useful? Okay, me personally, who knows? At Roblox, I don't really work at rendering much, if at all. I still like how do I put it? I don't think I don't write rendering code. I still work a lot with the team, kind of advising and suggesting kind of architecture and directional things, but I've barely written any code that was like hardcore rendering stuff in the last year or more. Maybe I'll do more. I think I'm actually planning to do a bit more Vulkan stuff in the next couple of months. But out of this specifically, so okay, like barring availability concerns, right? I already crossed out everything here, so it's really hard to read. So I think in terms of the short-term benefit, I'm really excited about depth stencil resolve because like maybe we can start doing some depth-based stuff on mobile, and that's gonna be cool. We'll probably hook up driver properties to do some reporting, but like not as interesting. If Imageless frame buffer was available everywhere, I would use this in a heartbeat to clean up like some really brittle code that we have. It's not, but like if it was there, I would use this. Not really interested in separate depth stencil stuff. We don't use stencil buffer much, if at all. So then, let's see. So from the Roblox perspective, and shader viewport index layer, like the last thing where you don't have to use geometry shaders, that's really, really cool. We had several prototypes internally that needed this feature, so that's great. So that's from the Roblox perspective. From the like, for example, if I wanted to take Niagara to the next level and build a fully fledged GPU-driven render out of this that goes beyond just geometry, I would use a bunch of these extensions to just clean up the code that we wrote so that it's just core Vulkan 1.2, and maybe we'll actually do that. So this is like 8-bit storage, draw indirect count, sample min-max, shader float 16 and 8 and all of this stuff, and the scalar block layout, which would be great because I can just, like, I know not all drivers support this and whatever, I really don't care. I would just enable this and I would just finally have this. I would like share structs between my GLSL code and my C code, and I can just change a struct and I don't have to. In fact, I think we end up, I remember thinking about this. Yeah, I don't think we share the structs right now. I think I moved everything in the header file so that in theory I could share it with C++ code, but I didn't actually share it. So I would actually like share structs, and I would be safe. I would know, okay, I'm adding an integer here. Nothing explodes in really weird ways because the C code and the GLSL code have different rules. And all of the bindless stuff, right? So everything that I'm talking about right now, I would probably rework some of the code that works with buffers to use the buffer address, because it makes it a bit cleaner, it makes it easier to reason about. I probably wouldn't have to write an allocator that like reallocates things inside one giant buffer if I use this. And definitely the descriptor indexing, which I'm going to talk about now, because without this you can't really do a GPU-based renderer that efficiently works with materials, etc. Or you can, but like it's not a great idea. You really need this extension ideally. Would this binder stuff allow different materials? Sort of, yes. So this is what I'm going to talk about. There's a caveat with the bindless stuff, which is that by itself it's not quite sufficient to do shader dispatch, but it's a great first step. There's like a second step, which NVIDIA has an extension for this second step, which is a bit similar, although a bit different. So I'm going to talk about this as well. It's not part of 1.2 though. All right, so descriptor indexing. So, okay, I just talked about how this buffer device address stuff is kind of revolutionary. It basically sort of is pointers on the GPU into the GPU buffer memory. You can have a pointer, you can read data from this pointer, you get values. Awesome. This covers all of the cases where the shader just needs values out of buffers. So this covers the geometry path basically entirely. What about textures? So specifically in the model, like if you look at the objects in Niagara, there's like a draw object someplace. There's like mesh draw, right, which refers to a structure that is representing, roughly speaking, a draw call, right? There's no actual draw call that's happening on the CPU per mesh, but it's a structure that corresponds to this. And so it has a mesh index, but it doesn't have a material index, right? And that seems to be a problem because materials are nice. Like we render everything with like a shader that outputs normals to the color or something like that, right? Like, I mean, okay. So what I actually want is I want another struct that is called material. And then inside this struct, I want texture. Let's just say texture pointers for now. It's not actually how it can work, but okay. Like texture objects, right? So I want to say, okay, I want an albedo texture, which is a texture. And then I want a normal map, which is also a texture. And then I want like metal rough and who knows what else. And I want some other things that are not textures. Maybe I want the roughness scale. Maybe I want some like index of refraction, which is like a float, let's say, right? Oh my god, wait. What you can see is that sometimes Microsoft Whiteboard misrecognizes my touch and just like moves the entire screen someplace and I have to restore it. So this is like a float, right? Maybe you have a buffer pointer here or an offset or whatever into some buffer that provides you some richer information about something. I don't know, like whatever. So you need a bunch of stuff. You need a bunch of values, and some of these values are floats and integers, and this is all fine. We already know how to do this, right? But some of these are textures. And so we have a struct that has some of this data, and then what we want is that we have a shader that runs, but we want the same shader to run because we can't in Vulkan yet change the shaders from the GPU timeline. So we can't say, oh yeah, there's a compute shader that will write shader IDs in some buffer, and then we will say I want to use this shader for this local. This is not a feature that's available. That will be one next big step in the bindless direction, right? But that's not a feature that's available right now. So it has to be the case that the CPU code says, here's a shader, draw things with that shader. In fact, if you look again at the Niagara source code, we do exactly that. There's like CMD bind pipelines somewhere, not in calling. Yeah, like we bind one shader. Or like there's multiple shaders here because there's like vertex, fragment, mesh, who cares, but there's one draw call, so there's a set of shaders, and then we draw everything. Now, we don't bind any textures here, but if we had to use any textures, what would we do is unclear, right? And so what we need to do is we need to be able to set a texture or texture ID, right? Here, really. And in the shader, we want to say, here's a texture ID. I just want to fetch data from this texture, like do a texture sampling operation, right? So how can we do that? Well, the answer right now is like it's really hard to build a full-fledged pipeline that uses this. Why? So there's one thing that you could use, which is texture arrays. But that doesn't work because texture arrays constrain your textures. They all have to be the same size, the same format, etc. So if you have like albedo textures, I guess all of them are like 528 by 528, 512 by 512. And that restriction doesn't work for this kind of work, right? What if you have two models and one of them uses a giant texture for albedo and a small texture for something else? Like, doesn't work. Okay, so one other thing that you can actually do in Vulkan, sort of, is arrays of textures. It's kind of different than texture arrays. Basically, in the shader, you say here's my like sampler, or I don't even remember the GLSL syntax for all of this, but let's just say here's a texture, and then let's say like I have an array of all textures, and then it has a size like 1024, right? And then you index into this array with an ID. Now, there's a couple of problems with this route. The first problem is most commonly the size of these arrays is limited to a really small constant on many GPUs, like 128 or even less in some cases. And so what we want, if you think about how many textures is reasonable to limit ourselves to, there's got to be some limit. But 1,000 textures is really not enough. 1,000,000 textures is probably enough. Like, it's unlikely that we'll want to render scenes with more than 1,000,000 unique textures. Some numbers in between have questionable values, some numbers are reasonable, right? So that's one problem. One other problem is ideally, when you compile the shaders, you don't even want to know what's like the maximum number of the textures. Who cares? As long as the CPU provides you with correct texture IDs, you can do whatever you want, right? But then, let's say that you have a giant array of textures. So there's like a giant array of texture descriptors, sorry. So it has like 1,000,000 texture descriptors. And there's a few interesting questions, like I load a new model. Can I take one of the slots in this array that wasn't used before and update it to the new descriptor? The answer right now is no. The answer right now is no. Let's just put it like this. Like, you can update a descriptor, but if the descriptor set that you're updating is in use by GPU, this is not even valid to do. And then if you have an array, if you allocated an array for like 1,000,000 texture descriptors, let's say it costs you like 64 megabytes of memory or something like this. 64 to 128 probably is a reasonable proxy. The question is, the first question is, do you have to fill all of them? Because you don't use all of them necessarily. The second question is, if you don't use all of them and you say fill them with like some things that aren't used, what's like the cost of dispatching a draw call with a descriptor set that is bound, that has 1,000,000 entries in it, but almost all of them are not used? And I guess there is one other question, which is, can you actually index this array in the shader? Because the semantics of this is unclear. Like, if in the shader you say, I want to index textures using the ID that I got from some structure, the question is, can the GPU do that? And the answer to this is complex, because what happens if this ID is actually different in all of the pixels on your screen? Who knows? And so Bindless or other descriptor indexing extension is kind of answering most of these questions. And here's what this extension allows you to practically do. So the extension has some limits. On some hardware, this limits might not be like good enough, but I forget what I think they are reasonable limits. And it has to be supported, even though it's in 1.2, as we discussed before, you have to enable it, you have to check if it's supported, things like that. But if it's supported and works and everything, here's what you can do. You can create one big descriptor array with a bunch of textures. You don't have to fill all of them. You don't only have to fill the ones that you dynamically use, meaning like if you never look at a slot in this array, it doesn't really matter. Then you can bind this giant array of textures once. And this is where the bindless term is slightly weird. It's not like we don't bind this, and it's not like we bind fewer things. It's like we bind all of the textures at once. They're in a giant array of descriptors. And then on the CPU, at some point, you can say, well, I kind of want to update the descriptor number 5 in this array to refer to this texture. And if the GPU isn't looking at that descriptor right now, then it's safe to do this. And you can do this kind of, as long as you do this before the GPU executes a draw command that has to read this slot, you're okay. Because in Vulkan, the way descriptor sets are designed is that there are different implementations. Some of the implementations look at the descriptor set and say, well, when you submit a draw call or when you bind the descriptor set or something, the driver at the point of submission will read every descriptor, do some magic operations with them, and then do some GPU state setup, which means it's kind of pointless to update the descriptor set after the driver has already looked at this, right? In some other operations, it's actually like memory on the GPU somewhere, so the bind of the descriptor set doesn't do anything interesting, but when you update the descriptor, it actually goes into the GPU memory and touches some bits there. And so what the bindless extension says is, well, your implementation has to be kind of the latter implementation where it's actually real memory somewhere on the GPU. When you update a thing, some bits in the GPU memory have to be updated. The updates follow the usual synchronization rules for any buffer data, as in you shouldn't do this while it's being read by the GPU. But if the GPU isn't using this specific segment of the buffer, you can do whatever you want with it. And the GPU can index this dynamically. There's one other thing that is related to this stuff, which is like non-uniform ext. But it's been 3 hours and I don't want to talk about this. It's a bit complex. But I'm just going to sidestep this. But like basically, this is what this extension allows you to do. So notice it's not quite as general as this buffer pointer stuff. Like you don't just get a 64-bit pointer to a texture and just get to use it anywhere. No, you have to have an array of textures and you have to index them by an ID. The array has finite size. Although you can decouple your shaders from this size, because now in the shaders, the spec says you can just remove 1024 and you can just have an unsized array, and it doesn't really matter how big it is, as long as all of the accesses kind of get into, use the descriptor that actually exists. So this is similar to, so in Niagara, when we did the geometry implementation, we had to create a big buffer, and then everything lives in this big buffer, and you get offsets into this buffer, etc. And so this is the same, right? So you get a big buffer of descriptors, etc. But with this, it's practical to do a GPU-side render implementation, because you can put all of your textures into this thing, and then you can use IDs to refer to them and stuff like that. The only caveat being that in an ideal world, there would be one more thing here, which is the shader ID. Because what if you have shaders that implement the GGX BRTF versus shaders that implement like some hair anisotropic model that needs some other data or some other code or whatever. So this kind of forces you to take one of the two implementation approaches in a renderer, right? Either you just have one shader, which honestly, I mean, for some cases it's fine, probably. Like you just have one shader that implements like PBR model with GGX and stuff, maybe like optional anisotropic or something, and you do everything else outside of this pipeline. Maybe this works fine. Or the other option is you can have multiple shaders, but then you have to kind of segment your dispatches. So instead of saying, here's one draw call that draws everything in my scene, you say, okay, let me bind the shader that renders PBR models with GGX shader. render all of them. Then bind the shader that renders models with skin shading, render all models with skin, all meshes with skin shading, etc. Which is still possible to do. It's a bit annoying. In some cases, it breaks. It makes it hard to render transparent objects. Like with this implementation, you can do transparent object sorting on the GPU and then just render all of them, but then you can't switch shaders. So it makes some things more annoying. It makes some things impossible, but it's a good first step. The good second step would be to do the same thing that we did with buffer addresses. That not we, I didn't really do this. I don't have anything to do with this, but and make like texture pointers or something like this. But the actual big step is to somehow enable dynamic GPU-driven shader dispatch. And Vulkan core doesn't have anything like this yet. There's an NVIDIA extension that sort of does this, but I haven't used this. All right. So I'm really tired, but we went through every single Vulkan 1.2 feature, not every single Vulkan feature. That would be impossible. And talked about what it does, why it's useful, etc. With the exception of subgroup broadcast dynamic ID feature, which if anybody really cares, if you used subgroup operations before, there is a broadcast operation that can take one value from all threads in the GPU, warp or wavefront or whatever. And if you don't know what these words mean, you shouldn't care about this feature. And broadcast them to every single lane. And the reason why this is useful is that on some GPUs, like AMD GPUs, it can use scalar loads and scalar operations which are faster. And so it used to be the case that you could only say broadcast, for example, like 0 or 5 or whatever, which is compile time constant. And now you can say broadcast n, where n is a variable that is the same across the entire lane, across the entire wavefront or warp or whatever, but dynamic. And this is useful because in some cases you can optimize code with this broadcast instruction. You couldn't do this before. But like if you didn't understand any of this, then you don't really care about any of this, because this is like getting into really arcane kind of GPU optimization territory with like knowledge about how exactly things execute in the shader cores and stuff like that. All right, so that is it. That is the entirety of Vulkan 1.2. That is the entirety of Vulkan 1.2. Does anybody have any questions that I should answer before we end this? Also, thank you for sticking around for all this time. Hopefully this was interesting. Yes, there's no shader dispatch yet, so yes, you have to do draw indirect. It's possible there's no geometry in the draw indirect. If you use draw indirect count, then the count is 0, right? And there's still a cost, but so then it depends. Like, I think if you have dozens of shaders, it's still fine. Like, this is still manageable, right? If you have thousands, then it's not really. And this is also why, so if you look at the ray tracing spec really closely, ray tracing spec actually provides a way to do dynamic dispatch, but it's only within the framework of the ray tracing, right? Because again, like this is what I talked about earlier, where you can't really do the old approach of rendering with ray tracing. You can't say, here's an object, like trace it, right? Like, no. Here's the entire scene, here's the ray, trace it, it hits an object with a shader, with parameters, with textures, like, shaded, right? And so within the ray tracing framework, there's facilities that automatically for you do magical shader dispatch, but none of this is exposed outside of the ray tracing framework. So there's like a way, there's clearly a way to do this on NVIDIA GPU, but nobody knows how it works, and nobody knows if it's general enough. With one exception of, so there's an NVIDIA generated commands extension. device generated commands extension, which again it's NVIDIA specific, but can you set? Yeah, so you can set a pipeline with this as well. So the reason why I didn't talk about this too much is it's kind of a different way to do GPU side rendering. The bindless rendering that I talked about, it's like, how about we just don't have draw calls, right? And instead of draw calls, we just have these giant, like, draw everything command, and then we dynamically figure out what data to pull from and what code to execute. Whereas the device generated commands is more like, okay, what if we had this traditional model where for every draw call there is bind stuff, bind shader, draw, bind more stuff, draw more. But instead of the CPU generating this, the GPU generates this. And it's also very interesting, right? It's a different balance. Like, it makes more things possible, but not all of the benefits apply, I guess. So if you want to play around with that and you have an NVIDIA GPU, you can try to use this extension, right? I have not tried to use that, but I'm assuming it works and it's probably good. But this is more about, without changing the architecture of your renderer, how do you move more stuff to the GPU? Whereas what I was talking about is more like, if you want to completely change the structure of everything, what would you do and how would you do that? And the Vulkan device generated commands obviously are not very useful in ray tracing world, right? So like, if you do bindless, ray tracing becomes much easier. I'm not even sure how you can do bindless without, or how do you do ray tracing without bindless? Because by necessity with ray tracing, you have to move all relevant information about how your scene should be shaded, etc., to the GPU in a way that's easily accessible from shaders and stuff like that. So that is that. Not really 1.2 question. Thoughts on MD memory allocator. I haven't used it. I know a lot of people who do. From what I know, it's great. You should use it. It's very simple. Like, I think the engineers working on this are super responsive to feedback, and the code that code seems to be production quality, and I think many games that ship with it. We don't use it in Roblox because when we ported to Vulkan, it wasn't a thing. It didn't exist. I don't use it in Niagara because by necessity, as you move more into these bindless solutions, you need a bit less of the object allocation and a bit more of this, like, kind of buffer management right now. But with the buffer address extension, right, actually it becomes more feasible to allocate more buffers and use them. So do you consider updating Niagara with description sometimes in the future? Yeah, so very possible. I kind of thought about this at some point, and then I decided to not do this, and then I kind of got burned out on Vulkan. And maybe the fact that I'm doing the stream means that I'm less burned out on Vulkan now, so we'll see. I think it's probably the case that I'll do a stream on Niagara 1.2 updates, just like little things here and there. The bindless indexing stuff would be bigger because we need to load models with textures. So we need to find like image libraries and model libraries and all of that. So it's a bigger amount of work. But yeah, like, I'll probably do this at some point. I'm just not sure when. Is it possible to move all the game logic on the GPU side? Yeah, I don't know. On one hand, as a person who is comfortable with the GPUs and shaders, my inclination is to say why not. But also as a person who read a lot of gameplay code and who has written some amount of this, not too much, and also who talked a lot with different gameplay programmers over the years, it's hard. Gameplay code tends to be messy, not easily optimizable, not easily parallelizable. For GPU code to work really well, you have to say, hey, here's 10,000 things that execute in parallel. For gameplay code, it's natural to say, well, this object talks to this object, which talks to this object, which talks to this object, and then this object updates in sequence because otherwise something breaks, so it's hard. I don't know. So yeah, I'm not sure about the game logic stuff. All right. Thank you everyone for watching the stream. It was great, even though it was super long, but it's fine. There's a long weekend ahead of me, so I guess I'm not doing any more Vulkan stuff, and I can kind of rest and take a break from that now. All right, thank you, and bye. Obviously, this will be on YouTube. It's probably on YouTube as we speak.